and this algebraic modeling language handles the translation of the math that you wrote down into whatever data structures or code that's needed to actually run some optimization algorithm, and it gives you the answer back. So here we have defined decision variables x and residuals. We add some linear constraints, and we add an objective. And here you can see, hopefully pretty easily, that we're writing a least squared regressions problem where the regression coefficients are defined to be within 0 to 1 and sum to 1. So this is a constrained optimization problem. We hand it off to IPOpt. We optimize, we get the solution back, and we return the value. So this is like JMP in a nutshell. What makes JMP interesting? Nice syntax. So because we're in Julia, we get to use this feature called macros, which lets us, if I go back, this at variable, at constraint, at objective lets us play around with the syntax and let you write something a bit more mathematical than you would if you were just writing plain code. So that's a feature of Julia. Comprehensive documentation. We've been working on this pretty hard for the past couple of years, and now we're pretty proud of it, although there's definitely always room for improvement. The community, as evidenced by this workshop today and all the discussions that happen online pretty frequently. JMP is open source, so you can use it however you like following the license. It's solver independent. We now list more than 40 solvers that you can connect to when you're using JMP. It's embedded in Julia, so usually when you're actually solving an optimization problem, you want to do more than just solve that one optimization problem. You might want to solve a lot of them in a loop. You might have some data processing. You might have some other logic. A lot of other things happen than just solving the optimization problem. And being in a language, fully featured programming language like Julia is very convenient for doing the rest of what you want to do besides just solving an optimization problem. JMP supports interacting with solvers while they're running. So this is a relatively advanced feature, but one that's pretty useful nonetheless. You can basically interact with the optimization algorithm in a way that, for example, lets you implicitly define constraints instead of enumerating constraints, just as one example. Another thing is JMP has low overhead for model generation. This is one of the original selling points of JMP. Compared to Python languages, Python-based libraries 10 years ago when we made these comparisons, but we're still working pretty hard to keep the model generation time under control. Finally, JMP is extensible to new solvers. So like we have 40 solvers connected. We didn't interface all of those. A lot of them were contributed by the community, and it's meant to be very extensible. Oh, and now finally, it's extensible to new problem classes. So we'll hear other talks during this workshop about how people have extended JMP in interesting ways. So JMP is developed by quite a large team. This slide is a reminder for myself to mention that a lot of most of what I'm talking about are not things that I implemented myself. I'm like the spokesman, but most of what I'm going to cover has been done by, well, Oscar in big part, Benoit, and the whole rest of the core developers, plus the more than 100 contributors that we have to JMP. So just to give some quantitative indications of how JMP is doing. So this is a plot of number of pull requests that have been opened against the JMP repositories over time. The slope of the line is interesting. It's basically how many new pull requests do we get in a given period. And we can, if we look between 2022 and 2023, looks like about 1,500 new pull requests over that time period. So that's quite a lot of activity happening. And another quantity that we like to look at is the number of unique users who have contributed to JMP. So we don't just want JMP to be done by a small number of people. We want we want a low barrier to contribution. So this line shows the total number of unique users who have opened a pull request, and that's pretty steadily increasing. So we do have a good flow of new people contributing to the project. So if you haven't opened up a pull request, you can be included in this line next year. Open issues by package. This one tells a bit of a story. So you can see JMP accumulated opened issues for quite a while, up until 2020. We had a small dip in before 2018 when we merged MathOp interface, but that was a relatively small dip, and we just kind of kept going out of control for a while. Then we hired Oscar through the NSF grant, and we've done a lot of work to keep this under control and manage our backlog of issues. And this is kind of a cartoon of kind of technology development. It's not a perfect fit, but I want to see if we can kind of impose the JMP story on this cartoon. So the peak of inflated expectations might be at the point where we decided we need to rewrite everything. So that was in 2017. After JMP had been around for a few years, we got a steady stream of feature requests. How do we do this? How do we do that? Like people were coming to JMP and asking us to do things, and we realized that the code could not do what we wanted it to do. So we decided to rewrite everything. Then maybe the trough is at the point where we reached 500 open issues. And it's a lot to manage, but in that period we did rewrite everything. And maybe today, my opinion is we're in a transition between this slope of enlightenment and plateau of productivity. So we are still developing new features, adding new things, but in a kind of cautious and conservative way, and in a way that is actually useful for people. So a few milestones from the past year. Between July 2022 and July 2023, we've released, gone from version 1.1 to 1.12. Maybe 1.13 will happen today if someone merges it. But we're very close to that. 2 of the 4 major roadmap items have been completed. Number of supported solvers increased from 37 to 43. The JMP 1.0 paper was published, so if you're citing JMP, we have a new paper for you to cite. JMP is now a registered trademark, the logo, so this helps us protect JMP from anyone who might be using the name in a confusing way. You might hear more about that, but for now we can just put that R mark next to JMP. We have some attention from the major commercial players. I won't say more on this, but if you've been following social media, you might know what's been going on. We also had our first JMP baby by one of the original developers of JMP, and maybe we'll have more as the years go on. Okay, in terms of technical improvements, I want to cover a few that you should know about. Multi-objective support, complex number support, generic number support, improved documentation, and reduced time to first solve. So multi-objective support is easy to explain. It was harder to actually get into JMP in a nice and clean way. So the syntax now is pretty straightforward. You define your variables, you define your constraints. You can also define expressions. And when you go to set the objective, you can provide a list of expressions that specify the objective. And this defines a multi-objective optimization problem. You have to use a special solver to do this, to solve this problem. I won't go into the math there. And what happens is that you say optimize, and then when you go to query your solution, you may be returned a list of multiple solvers. Each of those solvers has an objective value for each objective, and if you hopefully, if you're using the right algorithm, these will be Pareto optimal points. So this is a nice story about how this is a feature that was developed originally external to JMP in an extension, and over time we eventually integrated it into JMP, and now it's a has first-class support. Complex number support is another thing that we recently added. So this is a little tricky. What happens when you add a variable in the complex plane is you get an affine expression back, and that affine expression is the sum of two different variables, or the real component and the imaginary component. So under the hood, JMP creates two different variables, and we allow complex coefficients in these affine expressions. So you see it's an affine expression where the coefficients are complex numbers. And what you can do is then plug this into your favorite optimization problem that needs complex numbers. I've actually don't know much about complex numbers and optimization problems, but a lot of people like this. So what you can do is define Hermitian constraints on Hermitian matrices, like you would do in real coefficients. Write down the problem, you say solve, and you get the answer back. So that's complex numbers. They're useful. The biggest application I know is in AC power flow, but there are numerous other applications in kind of physics and engineering. Generic number support actually sounds very similar to complex number support, but it's an entirely different feature. Historically, JMP has assumed that coefficients are floating point numbers or complex expressions of floating point numbers. What we can do now is take a generic parameter. So here you can create a generic model, provide big float, and what that does is within the model, all the coefficients are big floats, and the variables are return values as big floats. So you use JMP, you define your variable. You can use just like square root of big 2 that gives you the square root of 2 in high precision, and you can toss that to your solver and get a high precision answer back. So that's pretty cool. This also works for rational numbers, which is useful for if you're maybe proving theorems and you really want to know the exact value of a linear programming problem. You can specify it in rational numbers, hand it off to a specialized solver, and get the answer back in rational arithmetic. So this is a long-standing feature that we very recently merged and will go out in the next version of JMP. Improved documentation. So there's been 7 new tutorials. We've integrated solver readmes into the documentation, which was a big coordination effort. Many miscellaneous improvements that I won't list. And if you go to the documentation and look at the PDF, it's over 1,000 pages. So there's a lot of documentation there. And we're continuously improving it, but this is one of the big efforts in the past year. Time to first solve. OK, so in the Julia world, there's a problem called time to first plot, or time to first whatever you want to do. In JMP, we call this time to first solve. So when you start up Julia, and let's just say you're defining a problem with 2 variables, 2 constraints, you call optimize. This should be very fast. You just have like 2 variables and 2 constraints. If you run this on Julia 1.7, it takes 10.5 seconds on my laptop, which is kind of slow. But the explanation that Julia users are very familiar with is the first time you run something, it's JIT compiling. The second time, it'll be very fast. We know that story, but it's also kind of annoying to wait 10 seconds the first time you solve the problem. So in Julia 1.9, this is now down to half a second. That's thanks to a lot of improvements on the Julia side that we've hooked into from JMP. There's still some compilation time. It may be, I mean, in terms of solving this problem, it's maybe milliseconds, so there's still compilation overhead the first time, but there's a pretty big usability difference going from 10 seconds to half a second. A few other things that you should maybe be aware of. There was a big refactoring for nonlinear programming, moving a lot of that functionality into the MathOpt interface package. This is in preparation for bigger refactoring that's happening soon. In terms of debugging, we have functions for relaxing constraints and turning them into penalized, relaxing constraints, moving them into the objective with a penalty, printing bridges, debugging what's going on with bridges. In terms of usability, we can now slice a sparse axis array. We have easy conversions to data frames. We can fix discrete variables. So what common request is, I'm solving a mixed integer optimization problem. Now I want to fix the values at their integer, fix the variables at their integer values, resolve that as a linear program, and query the duals. This fixed discrete variables helps you do that. Reified constraints is a syntax that we've added support for in our support for, which helps us add support for constraint programming. Vector valued inequality syntax is a change that lets you write like ax greater than or equal to b, and that will generate a vector constraint as opposed to ax dot greater than or equal to b, which generates a list of scalar constraints. So slightly different syntax that's useful in some situations. Who is citing JMP? So if you saw my talk last year, I gave a bit of an analysis of what fields are citing JMP and what they're using it for. This year I want to be more qualitative, so I took the 1,200 citations on Semantic Scholar and made a word cloud. So optimal kind of makes sense, and it shows you the major fields that are using JMP, so power, control, energy, systems, markets, electricity, hydrogen shows up there, COVID, a lot of interesting things, robust, planning, yeah, lots of words, and maybe not too surprising, but I'd say at least shows like power, control, energy shows like the big influence of JMP in energy applications. I also wanted to pick a few papers that just had very interesting titles. Policy making for oil imports by United Nations countries using a multi-objective mixed integer linear programming approach. That's pretty cool. Mixed integer linear programming for grain shipment in the Black Sea. Unfortunately, I don't know what's going to happen in the Black Sea, but it's cool that people can use JMP to make plans there. Multi-robot assembly scheduling for the Lunar Crater Radio Telescope on the far side of the moon. That's pretty cool. They're actually using JMP to analyze a proposed telescope plan, basically analyze the construction plans for a proposed telescope on the far side of the moon, and continuous time formulation of optimal task scheduling, quality of service assurance, and nanosatellites. So if you're in the aerospace world, people are using JMP for pretty cool things. Simulation and design of passive residual heat removal system for advanced temperature advanced reactor. This is actually a nuclear reactor, so people use JMP to design this heat removal system, which is part of a big engineering problem for bringing this class of nuclear reactors into practice. And then a few more traditional OR type applications, continent scale inventory routing, policy analytics in public schools, simulation and optimization package for emergency medical services. So all this is pretty cool. Like while we're here talking about syntax, fixing bugs, connecting to solvers, people are actually like using what we're doing for planning telescopes on the far side of the moon. So you have to be pretty proud of that. In terms of plans for the next year, it's a short list, but this is actually a pretty major point. The new nonlinear interface is probably our biggest item to handle in the next year, and will probably be tied to JMP 2.0. There are definitely more things that we can add to the list and more things that will come out of the discussions at the workshop this week, but nonlinear interface is a big thing. And with that, I will thank everyone and looking forward to the rest of the workshop.
So we have a few minutes for questions, plenty of questions. And the way this is going to work is we're going to ask the question, and then for the stream, I might ask that Miles kind of restates the question so that we can hear it on YouTube in the future. So any questions from the room? Jean-François.
So maybe I will be the devil advocate, but how much breaking stuff do you expect to be in Jump 2.0?
Okay, so the question is, what do we expect to break in Jump 2.0? It's still TBD, to be determined, but I would guess mostly anything that we need to break or want to break for the new nonlinear interface. There might be a couple other things we have in mind.
My plan is to try and get as much of the nonlinear in without breaking anything. So my hope is that we don't need to do a 2.0, but we'll see how that goes.
Yeah, but if we do 2.0, it would be because of the nonlinear changes, so the changes should be restricted to that, but maybe there's a few things that have been annoying us and we want to change also.
Yeah, like looking at the drafts for the nonlinear changes, I've seen that there's parameter support. Is that specific to the nonlinear changes, or is that something that will come to the linear and quadratic stuff as well?
Maybe this is turning into a question and answer for me rather than for Miles. So the question was there's always been nonlinear parameters in Jump. You can use the @nl parameter macro, and recently we added a new parameter set to MOI with the view to maybe supporting parameters in linear and quadratic functions as well. There's actually maybe even a talk in the next couple of minutes that will be maybe delving into that. So it's kind of on the roadmap, but no concrete plans.
There's a lot of other symbolic stuff going on in Julia right now, so like symbolics GLs, symbolics details, that kind of stuff. Has there been any thought of trying to, maybe unify or make compatible some of the stuff that's going on in Jump with the other symbolic stuff?
So the question was, there's a lot of other symbolic stuff in Julia, symbolics.jl, and plenty of other things. I would encourage you to come tomorrow to listen to my talk, where I might actually go into more detail on the nonlinear interface and how it actually interfaces with some of the symbolic stuff and why we've chosen the design we've chosen. So maybe I'll ask that we hold that for tomorrow. Any other questions, or should we all give Miles another round of applause?
Okay. Great presentation. I can look it up on.
All right. Okay, so we're gonna kick off in a little bit. So the next talk is from Jose Daniel Lara, who works at the National Renewable Energy Lab, and he's going to talk to us about some of the work they've been doing in Siena, which is power simulations redefined.
Yeah. Well, thanks, Oscar. Yeah. So this is the presentation today is about how do we model this kind of idea of co-located facilities with JUMP. So just to give a quick plug on the name changes, we have for the long time, maybe like 6 years now, maintained several packages in the Julia ecosystem to model power systems, both in operations and dynamics, and do plotting and different power flows. So basically, we are trying to create a large use and a scalable ecosystem of power systems modeling, and recently we renamed it Siena. Not the packages, but the capabilities that the packages contain. And today we're going to talk about the new capability we're creating that is called hybrid system simulations. So the first thing, for most of the audience, what is a hybrid system? Hybrid systems is one of the largest growing types of technologies being installed in the US right now. It's a new terminology to describe a behind-the-meter microgrid that transacts in the markets. And they have different combinations that could include solar and storage, could include wind and storage, could include other types of technologies like gas and storage, and it's basically a combination of different storage assets with different generation assets. These types of systems are, again, there's about almost 1 terawatt in the queue right now to be installed in the US. And there's some questions that operators and utilities are having about how will these assets operate. And what we have been observing is that a lot of these assets will operate what we call algorithmically. There's actually not an operator behind trying to come up and down, but they will actually be operated by essential optimization problems that run a portfolio of assets behind the meter. They do the trading in the market, and they decide how that operates. So for these types of systems, this particular project has been looking into 3 types of operation schemes to understand the impacts that they have in the system. So the first thing, this is the latest one, but so what we have right now is that a hybrid system actually is connected to a bus. We have our storage, we have our renewable asset, we have the grid, and we have a system operator that communicates with an energy management system that basically says, well, I put a bid in the market, and this is how you should deploy the assets behind the meter. So the operator doesn't have control necessarily over these assets. So the first operating model looks like this, where the system operator actually has direct control through the EMS and can tell the hybrid system owner how does he want the battery and the renewable to operate. And it's an optimization program that looks like this. You want to minimize the total system cost, and I've split the X variables between the total system variables and the hybrid system variables. Right? So there's a set of system-level functionality. Most of them are linear or MILPs. And there's a set of constraints for the hybrid system. But critically, the operator is able to minimize the overall cost, right, and communicates directly with the AMS. The second operating scheme is one that is closer to what we observe in practice today, where we actually have a hybrid system that wants to maximize a set of market transactions represented by Y. Those are bids into the market that are cleared by the operator. And it tries to balance out its internal cost of supplying its bids with it basically tries to minimize the cost of providing that power with the bits that it generates. and is subject to a set of constraints. So this model basically is a single operator. They send the bits, and it tries to balance out cost with the market transactions. And the latest model, the final model that we have is a model where actually the asset owner contracts a separate company to make the market transactions, and the separate company has to maximize its profits. It's a risk-taker company that then doesn't have control over the EMS, but the EMS of the asset owner still receives the signal from the market. So in this case, we want to maximize the profits, but now we're subject to minimizing the cost of providing those bits. How do we supply those bits? That's generally speaking the three types of models that we're seeing, right? So in the experimental setup that we have, what we have tried to do is to say, well, we're going to generate some price forecast, create a bidding problem in JUMP, pass those bits into a market clearing engine in Siena. Then we can actually lock those bits or fix those bits and run again the real time to see how the hybrid adjusts to the updated bits and the updated forecast, run the adjustment period, and then compute the revenue part of the hybrid system. So one of the key elements of a hybrid system is the fact that it's flexible. So we want to be able to say, I made a bid in the day ahead with the forecast. Now I have to rechange my bid in the real time, given what I got awarded in the real time, in the day ahead, and the new forecast. So the first set of results are for energy-only products. We're going to leave out ancillary services for now. So here, there's a lot going on in this plot, but because I only have 10 minutes, I put a lot in a single slide. And here we can see what the day-ahead bidding result looks like. We can see here, this is the prices of the real time. This is the forecast issued at the day-ahead time of the real-time prices. So this is what the asset owner thinks is going to happen in real time. So we can see it here charging the battery, and then discharging the battery when the prices are high. We can see the SOC going up and down. We can see how at particular hours, especially with negative prices, is charging the battery, and in some cases actually turns on a thermal unit to charge the battery because it's convenient. And we can see how the battery gets discharged in these blue blocks precisely where the prices are the highest. Right? So we can see that and then here we can see the interesting effect. Because there's such a price negative value here, it actually decides to curtail the wind power and operate the thermal unit in order to charge the battery. And if we zoom in here, we can see there's like a small increase in the use of the storage here, precisely because it's getting paid to consume power. Right? So that's basically what we can see from the day-ahead bidding results. Now we can see the effect on prices. So if we actually take the centralized prices for the day-ahead, which is this blue line, if the asset is operated by the operator, thinking that it has to do the best for the system with the first optimization model we see, we can see that the prices follow this blue line. Now, once the assets operate in the second model, where they can actually try to optimize their own benefit, given the price forecast, we can see that they cause price collapses. And this is kind of like a QA/QC that the model is doing the right thing, because this is what we observe in real markets. Assets that try to maximize their profit usually tend to collapse the prices because they push power at the times of they're not convenient for the system, generally speaking. And then we can see the effect on the real-time prices. So again, this blue line is the forecast used by the asset to produce its bids. And we can see here the effect that it has in real-time prices also causing some price collapses and some important differences reducing prices. And then in hours, when there's actually not that many renewables for the hybrid, we can see that the prices are well aligned. So here we can see the effect of strategic bidding and algorithmic bidding in some of these energy systems that operate in this fashion. So now if we go into the co-optimizer, now we're working on actually implementing the ancillary services market. So I don't have price results yet, but here we can see now a co-optimizer strategy that actually tries to allocate ancillary services products too. We can see here what the actual output power is and the preference for the price profiles that we have of providing regulation down reserves and a little bit of regulation up. And this is important to remember for some of the latest slides. So here we can see the asset basically preferring to bid on energy, bidding out in this red line, and then not providing too much spin reserves, right? So it provides spin reserves when it's charging the battery that it decides to actually acquire power. Now, the interesting thing that we're working on right now is this bi-level strategy in understanding the effects of a lot of the business model that are happening when these assets are leased to other operators. So we have this model that we had before, where we're subject to some of the market constraints, and we want to be subject to minimizing the cost of supplying this market value. So this is your classical reformulation, where you end up with this bilinear for the stationary conditions and the optimality conditions. And we implemented it basically using SOS constraints and substituting here both the stationarity condition with the classical SOS format and implementing this additional cut where we substitute the variable y for the bits with the upper bounds of the y to improve computational speed. And the outcome is we have the same result. And the reason for this actually is part of some of the conclusions that we're going to arrive. And the reason why we see this is because the value of these bilateral problems actually depends on the relative effect that this y has down here. So because we can see that there's not that much market participation in the ancillary services, then the relative value of changing the results because of that y then is very minimal. So, and then we're working in new developments to integrate ancillary services offers into the hybrid system and modeling the markets around that. And finally, this research was sponsored by the Department of Energy and the Grid Modeling Lab Consortium under the Flex Power project. Thank you very much.
Thanks, Jose. So we don't have any time for questions in these 10-minute talks. So I might ask that we will hold those questions to lunch. So next up, we have Stefan, who's going to be telling us about more energy-related modeling. And this relates to the parameter question. So I came to meet Stefan when he banged on my door and said, I'm trying to build very big jump models with parameters, and it's not working. What should I do? And so the person to talk about parameters is Stefan.
Thank you. Nice. Perfect. It works. Let me just quickly pull it up into full screen. All right. There we go. So, yeah, thank you and welcome to my talk. I'm not going to share any results today. I'm more going to be talking about what we learned and what we didn't learn during our journey with JUMP. And so a quick start. Give me a second. There we are. So what am I going to talk today is TESCA, our Techno-Economic System and Component Analysis Framework, and specifically TESCA Optimizer, which is the optimization tool behind it. So preface, TESCA Optimizer will hopefully be open source soon. We're talking about this for a couple of years now, but will be soon in the future. So I want to begin with what it is and some of the key facts. Yes, it's an energy system optimization framework, but the interesting part is that we're using it for vast different models. So we're using it for low latency model predictive control, meaning there's a few milliseconds to solve each model, where it's about milliseconds to rebuild the models. But we're also using it for continental scope models, where we take pure LPs that take hours to days to really solve. So we replaced a lot of different tools, but this one single thing here. And so what are some of the features? One of the most important ones that we're proud of is that we are able to describe arbitrary energy system models using YAML and CSV files. So there's no coding involved. And even if you want to create new energy carriers, if you want to create new types of devices in your system, you can create those devices using YAML files. And why is that possible? And that's probably our biggest achievement, is a kind of abstract block structure that we use. So we're not talking in energy system components, but we're talking in abstract building blocks. And you can take these different building blocks to combine them into bigger things. So for example, you could use them to define a heat pump in a small household, but you can also use them to define a large-scale nuclear power plant. And why is that important and why is that interesting? And that is mainly due to the next fact that we can define various things, like, for example, decomposition approaches, stochastic optimization, or other cool things like time series aggregation on these abstract building blocks. And then they immediately scale to any kind of component that the user wants to define. So you don't have to do decomposition approaches again for different types of energy system components. We have them built into the abstract core blocks. So, but onto our learnings. And I want to start with why we're using JUMP. And pre-phase, we were really not happy with using JUMP when we started out in 2021, because there were a lot of hurdles to overcome coming from a super object-oriented programming style and thinking about models and then transferring that to JUMP. But the thing is, JUMP was way too fast in 2021 compared to other alternatives, so we had to use it. And now in the end, we're really happy that we chose it, because the thing is that with the performance comes the possibility to like slim down our code base. I've just checked, so all of what I'm talking about today, we have around 10,000 lines of code, which is really, really small for an energy system model. And that is only because we can forego some of the optimization in the code base, some of the performance in the code base, because JUMP itself is so fast. And I want to point out two things. We heard something about relax with penalty already today. So the two things that happened really for us was the first thing was a large problem with garbage collection in the string names that we had. And now there is the set string names on creation function that you can use to globally disable string names. So you can build readable JUMP models while still then having the full performance at hand if you actually need it. And the second one is the relax with penalty, and that's fairly new, if I remember correctly. And so the thing is, we had soft constraints from the beginning on. That was one of the crucial points of our model, that we enable our users to use soft constraints. And then the relax with penalty function came out, and that is a performance loss. So our manual implementation of that was a bit faster, but the thing is, it convoluted the code and it was really not readable. And relax with penalty is an easy approach to relax your constraints with penalty in the objective function. And so we essentially refactored our whole code base to rework that to use relax with penalty, because in the end, it makes it easier to maintain the code base, easier to read, and easier for other people to get into it. So it's really cool to see, like the last 2.5 years, how much JUMP has developed and how much there is to actually use for us as model developers. So it's not just a framework, but it's really something that you can really use. We heard about the parameters, so I'm probably going to be specific about this here. So one of my biggest interests is always left-hand side, so multiplicative parameters. And the reason for that is I mentioned low latency model predictive control, for example, and it's really important that you can efficiently modify your optimization problem if you're doing iterative solves. And this is something that's really not possible in JUMP. Yes, of course it's possible. We have different solutions, but the problem is JUMP is so fast that you don't want to really slow it down with some slower thing. And so a lot of the different possibilities to include parameters kind of leads to quadratic expressions in some way or the other, because in the end you have to keep variable coefficients and you have to keep parameters. And so it's slower than you would actually like it to be. Maybe that's part for future contributions. We have a new one in the pipeline we call sparse expressions. Let's see, it's probably going to fail too, like the other ones before, but we're still trying. And other things would be like, for example, SOS1 and SOS2 reformulations. I've seen that there was some interest in the past regarding that. Maybe that's something that we can contribute as soon as Task Optimizer is actually open source. And the Techify JL, I'm going to cover that later on. All right, and I promised some learnings. So if you're interested in parameters, talk to me later, because I can talk hours about parameters, but learnings. So thing one is memory usage. Memory usage is something that's strange, because coming from other energy system modeling tools, you don't care about memory. It's all about performance, about timing. You really run out of time building large-scale models. You don't run out of memory. But now the problem is, like, JUMP is performant enough that you actually start running out of memory before you hit timing limits. So other models, they can't build on my laptop in a reasonable amount of time. JUMP can really do that, but now I'm running out of memory here. And so this is one of my personal interests and active research as a PhD student, is how we can actually apply various tricks, for example, decomposition, that like most people here probably know, but are really underused in energy system research, to achieve some kind of trade-off between performance and memory usage that actually allows people not familiar with these topics to actually just use it as a tool. Second learning, and maybe that's the most important one here, is usability first. So we're building a tool, we're building an energy system model, but it means there are actual people using that to create models. So we're not doing everything our own, so there will be users. And the thing is, users will not always be developers. To be fair, most of them are not developers. They may not even come from a technical background, but they're used to tools that just work. And the thing is here, maybe your tool that you're building is way cooler than the tool they're using. Maybe their tool is even bad, but they don't care because their tool works. So you have to produce a tool that actually just works. And so how do we deal with this? First thing I already mentioned is the no-code approach. You can do everything using YAML and CSV files. The second one is graphical user interfaces. That's super helpful because that draws people into your tool. Next one is probably not the right conference to mention it, but you actually need a Python wrapper, and you need to communicate people what it means to use a Julia tool in the back end. Yes, we have the time to first solve that's really improving, but it's something different, and you need to communicate it to build trust. Trust will be my learning number 3. But regarding the graphical user interface, I've inserted a short plot here because I heard that there's some interest in that yesterday. So what we can actually do is, I don't know if you know Draw.io, diagrams.net, whatever it's called right now. So we have a possibility that the user can draw arbitrary diagrams, like can insert text and new figures and whatever. We can hide all of that. Just pick the stuff that we're interested in. We can actually convert this here into a full energy system model. And this is really cool because you don't need to write YAML files anymore. No coding, no YAML files, just drawing diagrams. And onto my last slide. So trust and correctness. One of the biggest problems with that is always how can we test optimization models? How can we ensure that they're correct? And I want to highlight one of the most important ones, and that is Techify. And we are really proud of that. That is that we can convert arbitrary jump models into LaTeX code. And this is really cool. You can see here that some of this is getting lost. So for example, here's Slack with a question mark. That is a variable inserted by Relax with penalties. So we are losing information here. But in the end, you can still see that's a lot cooler than doing a print of a few thousand constraints because we can actually figure out how the mathematical description could look like. All right. Thanks, and any questions then later on.
Thanks very much. We actually had at one point a tech print that tried to be clever, and we removed it because it was too complicated to maintain. So we'll have to go and have a look at that. So up next we have 2 related talks from SINTEF in Norway on more energy system modeling in JUMP. I hope you're still keen for it. The first one is Truls.
Okay, you can hear me. So this is a short talk on a new package we are developing, not released yet. So to prove that it's still working, I'm running this in a notebook, a live notebook. So hopefully, cross my fingers, and it will work. So this is a package that can be used for time structure modeling in JUMP. So it's a joint work with my colleague Lars Hellemo at SINTEF. So I'll just... So yeah, so we work at SINTEF, a large contract research institute in Norway. And we've been working quite a lot with MIP models, large MIP models in various applications. And for the last few years, we have turned a lot of these models into JUMP, sort of by the promise of sort of this flexibility performance. But for us, one of the key points was the availability to make more modules, because we were tired of these huge monolithic models we were doing in most of like 15, 20,000 lines of code, and it's a hassle to keep up with. So one of the things we were facing then is to try to make smaller packages that supports a specific functionality. And one of the first things we started with was to look into the time modeling, which is quite a simple thing, but it can grow and be more complex as you go on. Because a lot of real-world optimization problems involve planning over multiple time periods and also different time scales. Typical examples are long-term investment models, where you combine it, so you have to make strategic decisions based on operational modeling with short time frames, varying time durations. So that's our motivation. And the motivation is here sort of to ease the model development, to enable code reuse, and also to less development time. So what is the basic idea is that for us, a time structure is then an iterable sequence of time periods. Fairly basic. And then you have time profiles that provides values indexed by those time periods. So that's sort of a very simple idea. And we was playing on along and see what that will lead us. So could we make a well-defined API on top of those ideas, and to make sort of a package that lets us make optimization models independent of the time structure that you use. You could be flexible in what kind of time structure you want to use. So basic time structures are like these, fairly simple ones. So you can have uniform time periods of uniform duration. You could specify the durations, so have varying time duration. And you can also do things involving calendar time. So having calendar arithmetic, for instance, could be in some applications. So these are the building stones. And then you can do multiple time scales. So you have 2 levels. You have these green ones here, which are at a strategic level. And under these, you can have more operational periods, reusing those structures, those basic structures, in a 2-level approach. So here you can see that you have 4 strategic levels of a certain duration, and in each strategic level, top level, you use a simple uniform time representation. And then you have the time profiles that provides values for these time periods. So you can have, for instance, fixed profiles that have just a fixed value for all time periods, whatever. And you can have operational profiles that has a value that varies with the time period. And there are even, we have even more complex ones when you go into 2-level structures with strategic profiles, and you can also have scenario profiles. I'll show. So I'll just quickly show that we also have more complex time structures that work with the same API. So you can have multiple operational scenarios. Typical in, for instance, solar and wind applications, you do not know what the wind is going to be, so you may have multiple ones with given probabilities. So you're closing in on stochastic programming approaches. And you can also do scenario trees with these, sort of combining these basic structures. So here you're combining the operational scenarios with the basic simple times into more. So you're building upon and always having well-tested underlying structures. So and then you can be quite flexible. So you could sort of, see if I can do. So for instance, increasing the number of scenarios. You can play along. So you can start out with very basic structures, and then you can introduce more complex structures without changing your optimization model to a large extent. So how does this look in JUMP? So there's a basic example. You define your periods on top there. You make some profiles. And then you can index your variables directly on these time structures. And then you can do iterations. So this time period structure is an iterable sequence of time periods. So you get a very natural modeling of things. So it's fairly easy, and then you can start out with very simple time structures, like here, with a simple, like 2 time periods. And then it's easy, sort of, your model, then it's easy in the development. It's easy to debug. You can start out with a fairly simple structure, fixed values for your profiles, and then you can extend things. So it's sort of keeping your model the same, but you can go on to more and more complex time structures. And if you want to do a 2-level, the previous one was more like a battery model, but on a strategic level, you want to set your capacity at the correct level. I guess it's hard to say, but it's fairly then simple to, you just keep your operational model as it was, and you just introduce a new variable there, capacity, that is indexed by the strategic periods of your time period structure. So that's just a function in the API here. And then you add a constraint that sort of says that the state at each time period is less or equal to the capacity. And then the other constraints are just the same as you had in your previous example, where you're just looking at the operational side. So yeah, and then you can see that you get a more complex model. And you can play, so it's fast here to start out simple, but you could sort of change your time prof structure dynamically and see what happens. So to summarize, I've presented a package for high-level modeling in JUMP to facilitate code reuse. I think sort of there's a benefit of Julia and JUMP to get these more generic packages to simplify the modeling. And I think there's quite a lot of potential for this kind of more high-level modeling than we're seeing in JUMP to get code reuse among different people. So we're not looking at time structures. We are also working a bit on storages on top of that, for instance, as a more generic concept, and also investment strategies. So the package is not registered yet, but will shortly be available on an open source license, hopefully in August. Holidays in Norway is a serious thing, so July sort of came a bit too quick for me. But yeah, but if you're interested, just come and ask me, and I'll show off things more. But it will be available in August, hopefully. So thanks to all other who contributed, and also financial support.
Thanks very much. I've implemented far too many times the same time stage thing and never refactored it into one package. So up next, we have another 30-minute talk on energy system modeling that hopefully uses the stuff that we just heard about. So there's a mic that we need to put on. So, yep.
I guess now I'm in. Perfect. No, it's fine.
Now we have Julian to tell us about designing an energy system model from SynTef.
Yeah, hello everyone, and thanks that I'm able to talk about it. I don't have to present about SynTef. Truls did that fortunately already for me. But a bit about background. We wanted, or that's part of the project for the energy export from Norway, or decarbonized energy export from Norway. Quite a lot of energy system models so far come from either operations research, industrial economics area, or from the power system side. I'm a chemical engineer. For me, the approach is slightly different because chemical processes are slightly different than power processes, and to have that properly implemented. Now, to first talk a bit about the ratio for the development, if we take a look at the current energy system models, and here we have the high-level models like TIMES, Genesis Smart, we have a power system, we have extended power system models, and all of these ones are normally developed in a proprietary language. If you have looked into TIMES source code in GUMS, it's rather painful to try to understand what is happening. The same for Genesis Smart, and they are also quite difficult to extend with a slightly different technology description compared to what you have in the standard input-output process. One problem here is that the energy system, energy balances are normally not solved on the technology level, which implies that adding something or new technology descriptions for proper CO2 accounting, deactivation in batteries, and degradation in electrolysis is rather difficult. Furthermore, in these models, you have all regions which you want to model are treated in exactly the same way. You have parameters which then say, okay, we can't invest in a given region, offshore region, into, let's say, a nuclear power plant. But it's still quite heavily parameter driven. And we wanted to get away from that. And if you take, on the other hand, extended specialized models at NTNU in Norway, they work quite a lot with Empire for multi-stage stochastic optimization problems. And they normally focus on a single energy carrier. And if you then extend it, it's essentially an in my opinion, most of the time an unconscious bias. So essentially what you do then is you have a full model for, let's say, power, and you add to said power model hydrogen. You treat the different energy carriers differently. And that is not necessarily then leading to a good process. So our aim within that project is, when we realize we don't have any model which is able to solve that, what we want to solve, is that we want to have absolute flexibility with respect to time description, technology description, and investment modeling. The time structure part beforehand also originates partly out of that said project, and it's actually one of the applications where time struct is used extensively. And all of these flexibility we want to achieve without any changes to the core structure of the model. So a person working with it has to a certain degree, understand what is happening in the core model, but does not have to change anything there. And that essentially leads then that we move away from a kind of parameter-driven flexibility where you say you specify different parameters, which is also extensively existing, to a kind of type-based flexibility. Now, to give you a bit of an overview, Truls mentioned before, and that we are quite happy in CentOF to move away from monolithic models and instead have individual packages. The time structure package was one of the original packages which was developed here. And the time representation makes it, we took it out so we can reuse it for pretty much anything we want to have. Different models, be it for energy system modeling, be it for any other supply chain modeling. And we have one base model. And the base model is pretty much providing the framework of the system. These combination of these two models are normally, or is required for the overall framework. And the base model corresponds to an operational model, can be multi-time periods, but without any geographical features, without any major technology descriptions. It has a standard technologies representations in it, but it does not have anything specialized. And on top of that, we then can set a geography package, which allows for investment in transmission corridors, transmission modes, different description, whether it's pipeline transport, mixing of hydrogen and natural gas as an example, and also for investment modeling. And the last point, which at least for me as a chemical engineer is rather important to include, is specific packages for the individual energy carriers. And all of these ones here can be developed. We have a few ourselves. We're looking into mostly CO2 and hydrogen for us, but it also is possible to use whatever you want, develop something on top, and just reuse the base structure. And all of these, one is working through Dispatch, which most of you attending JuliaCon obviously have quite a lot of knowledge about. And another point which was rather important for us is that it's rather straightforward to understand how the model is built up. So the overall flow structure to understand what is called when, how you can reuse parts of the code which was developed beforehand, that all of these things are there and easy to follow. Now, that is the overall modeling structure. Let's go a bit more into, let's say, the technology descriptions and what we can do there. For those of you familiar with energy system modeling, you always have an energy source, energy sink, and energy node. For us, we implemented all of that with abstract types, which allows us to essentially then use that for the individual dispatch for the different functionalities for that. And if we want to have a specific technology, we use composite types, allows us then to have the parameters specifically for each technology. And similar to what was presented beforehand, we also use YAML files for providing the technology input there. For the overall point here, and now I have to zoom in a bit because I think that is rather small to see. It's essentially for us, we use a classical time structure point, but the key point is that for each new technology you want to have, you pretty much have to define two functions, and that's it. Two functions and a type. And let's zoom out again. Quite a lot of these things can be also reused. Standard mass balance or flow in, flow out for an energy system is pretty much independent, or most of the time independent of a given node. So in that respect, we also have a further workflow for constraints functions, which allows us then to reduce the number of lines we require and focus instead of reusing what was done beforehand. And we implemented these functions for quite a lot of different key technologies. We have standard sources, sinks, conversion units, storage units, but we also use it for other technologies. That one here, to zoom in again, is just showing a bit how we can calculate the constraints functions, which are then here. For example, you don't see for the capacities something specified for network or for sources. Instead, it just uses the standard node. So the overall type hierarchy allows us to reduce then the structure. And the first time I'm actually using Zoom, so it's a bit of a mess. And we implemented that for quite a lot of different things. We had the capacity constraints. We have the variable OPEX or fixed OPEX constraints. So essentially, it allows us to also work on specific technologies. One key point which we have not yet implemented, but it's a part for the near future, is also for the stochastic versus deterministic analysis. Truls showed you the two-level structures beforehand, where you can have several, let's say, representative periods, and that we can also pretty much then change on the level where it's required, where you have a constraint which is dependent on the previous time state. So essentially, you do not have to do any major changes if you want to implement that. Pretty much just the function changes. Quite a lot of these things could be also solved in Python PMA using object-oriented programming. But then again, you could have an explosion of possibilities and couplings, which is way simpler to do that within Julia. To give you a few examples, what we have implemented here for our project is for CO2 storage units, because most of the time CO2 storage is different in accounting of the total stored volume compared to other technologies, because you have the total limit. And if you say for the next 25 years, you have to have an upper bound which can be filled really fast early or really fast late. And that implementation of this technology takes 1 hour, and then writing 5 hours of tests that it's doing what you want. But we also have, coming from Norway, quite interest in hydropower modeling, how the hydropower flow is working to implement that properly, and for electrolyzer degradation, what leads to bilinear terms, and is a bit of a problem, but still solves. Now, talking here about the extensions, we only need, for writing a new package for this, we only need to have a dispatch on the node type. And as I mentioned beforehand, if you want to introduce a new technology description, be it a heat pump, where you have dependency on the outlet, outside temperature, or CO2 storage nodes, you pretty much only have to formulate a new composite type and 2 functions. So in that respect, moving away from the standard input-output efficiency approach in energy system modeling is rather simple in this situation. And so here is one example looking into a non-dispatchable renewable energy sources. What we do here is pretty much taking a look at these functions. The composite type, variables creation for the individual nodes, which we're currently doing for all non-dispatchable renewable energy sources in the same kind, plus the constraint functions for that. And that is pretty much all needed if you want to have a new technology descriptions. Nothing more has to be done. Similarly, you can also dispatch purely on the constraint function, which I have not shown here. So you don't even have to go too much into the overall system if you trust that the mass balances and so on are working in what we have done beforehand. You pretty much just write new capacity constraints. And lastly, none of that here requires any changes to the core structure. So to give you a bit of an example, it's what we are looking into. It's essentially a demand where you can either use, let's say, hydrogen or natural gas equivalently, although it has an impact on the CO2 emissions within this demand. To write that change was a small change in the constraint function, a new composite type. That actually took me only half an hour for that case study. And then, again, 2 or 3 hours of tests, and it was there. And when I was working with other models beforehand, you're always required to have to do some changes in the core structure to extend things. And we also have in the different composite types, which are describing the individual nodes or technology nodes, a wildcard data type, which we plan to use slightly more in the future. One thought process is here that we want to use it for LCA functionality for the individual technology nodes, or we use it as well for investments at the time being, but it allows something to put on top what is existing so far for new features. And then again, the type usage simplifies that we can use the proper function which we want to. And that is not really easily doable in other technologies. And as mentioned, can be separate functions, for example, for classical LCA analysis. Now, that is pretty much the approach, what we can do for different technology descriptions. It's most important, in my opinion, for things where the standard approach may fail. Let's say battery degradation, where it's, if you consider it or not, has an impact on how you operate it. Similar electrolyzer degradation. And these things can be fast implemented if you know what your model should imply. Currently, we're also implementing a direct air capture unit model. And it's rather straightforward and simple. Now, the second part, I want to talk about investment options. There will be most likely quite significant changes happening here. We were also, while we were here at the conference with our colleague Lars Truls and I, we were in contact and thinking about the further development. But to give you the classical challenge for investment modeling is that in most of the models, you have a single investment option for all technologies. So either the model is based on discrete investments, or it's based on continuous investments. Some of them also have piecewise linear for economy of scale included, or learning curves, but it's most of the time it's an either or. You choose what you want to have. Now, you want to be able to have the possibility to change investment options for different technologies. For those of you familiar with these technologies, if you have a natural gas reforming with a CCS plant, they are normally in the range of 800 megawatts plus, because they have a significant economy of scale. So in that respect, it makes sense to have an integer investment, discrete investment for that technology. On the other hand, electrolyzers, excluding balance of plant, purely electrolyzer stacks, have way less economy of scale. It's essentially in this repetition. So if you reached 100 megawatt, they're pretty much multiples of 100 megawatt. Wind power, largest one, is currently in the range of 18 megawatt. So if you're talking about gigawatt installations, you can treat it as continuous. But on the other hand, you also want to have the same technology in each region, the possibility to change whether it's continuous, discrete, or how you want to model that. So let's say we have a smaller wind farm potential here. It makes quite a lot of sense to have it discrete. Well, if you're looking into Norway as a single node, why should you bother about these integer variables? And to give you a bit of an overview what type of investment options are generally existing, we have the continuous investments used in times and most of the really large-scale models, because otherwise you can't solve that. We have semi-continuous investments where you have a lower bound. We have fixed investments, which pretty much just say you have to invest in it or not in a fixed capacity. And the discrete investments, which I jumped over. And for us, we want to pretty much decide on the model creation part what type of technology should be utilized for that. And the investment package at the time being is an extension to the base package. It's going to be potentially also more independent like TimeStruct, so that the overall investment implementation is openly available for whatever model you want to utilize it. And key point here is, for the time being in the implementation, that we're looking into an energy model, which can be an operational model or an investment model. And that is, these types pretty much include all the global information which we have generally available. And again, so it's essentially, if we have an investment model, we overload the function from the base to pretty much just include the investment constraints on top of that and create the variables for the investments required only for the technologies which have investments. And that can be also, yeah, pretty much just an overloading small part on the model type, and that works neatly. And the similar approach which we have for the investment options in itself, using that based on type structure. And in that respect, we pretty much have we have a simple approach where we do not have to copy code from one point to the next point. We pretty much just reuse what is existing already beforehand and only change the parts of the model which require to change. And we have a similar approach as well for the lifetime of technologies, because most of the time, if we have a time structure which says we have 5 investment periods of 5 years each, total 25 years, and a technology has a lifetime of 18 years, it's a bit always a discussion. How should it be handled? When should it be retired? And that is also included different ways to see for the lifetime. So you can specify that for each technology in each individual region, however you want to do that. And now we are coming here at the point where Julia strives or is amazing for working with that, because with all the different technologies which we have and all the different lifetime approaches and investment options we have, we end up with the potential for, or have a huge potential of combinations of the individual technologies with different investment options, with different lifetime options, and even write new technologies. Now, how do we see it with a way forward? And as I mentioned before, and we have quite a few packages already developed. They are currently internal still. It's a bit of more difficult in this project to publish that, also due to industrial partners. And as Truls mentioned, it's impossible to reach anyone in Norway in July. So it is an issue, but we prepared it in a way that I hope we can have it open on GitHub in August. That is actually my biggest point. And we have geography I have not talked at all about, but we have also a geography package which allows for different areas, transmission corridors between set areas and transmission modes. So specifically, you can limit what is allowed in between. You can have then also contrary to what is done in quite a lot of models, you don't have to look into the cost per kilometer, but you have the specified cost, differentiate onshore, offshore, all these things easily doable. And the interesting part is as well with the areas that you can add additional constraints on different type of areas. So saying that from a given area you can not export too much. That is in Norway a rather interesting discussion right now due to the energy crisis in Europe. And most of the approaches which we follow in geography are similar to the base package. So if you understand the base package, you understand how it's done in the geography package. And we have also quite a detailed description included within that project for non-dispatchable renewable energy sources, pumped hydropower or classical hydropower, electrolyzers with degradation and stack replacement, which complicates it quite a lot because it leads to bilinear terms which cannot be avoided. And also CO2 storage with proper accounting of the total storage volume. Now, when we look into the future, that model, or overall the development, comes from a project which started in initially 2019, coding started in 2020 on this part, but it's replacing other models which we currently have at SINTEF within energy systems, and also simplifies future development. And there are quite a lot of projects in the pipeline starting right now. And what we also want to include, or what I directly want to mention, is that we have this data type. Currently, it's used for investment models, and it allows us for easy extension of the overall system. So essentially, for each technology, that you have the possibility to extend on the description of the node, that you can have LCA calculations included, depending on what type of data you provide. And it's not necessary that everything is provided to everything. You could choose based on the technology. And similarly, we want to have a few things like dependencies between investment options. You have to retire A before you can invest B, which is, in the current framework, takes a bit of time to think about how we can include that best. And also work a bit more on further flexibility for variables which we consider to be global for the system, like emissions and constraint calculation for these ones. And lastly, second lastly, as said beforehand, for broader user base, it's rather important to have it easy accessible. For me, to create a new case study goes really, really fast because I know the model and all the parts of it. For others, it can be a bit more difficult, but that is going to happen as well. And the most important part, actually, in my opinion, is release of the packages on GitHub. It will happen eventually, hopefully in August. We have that also signed with the Research Council of Norway that we have to release it, otherwise we would not have gotten the project. We started also working on it, but the holidays somehow put a break in it. And lastly, I would like to thank the project partner. It's quite a combination of different energy companies in Europe, and its overall development team consists, of 8 people, 7 people. It's depending. We get more and more people working on it, and the GitHub link so far points towards the project where we're going to upload everything. It already has a README. The only thing missing are still the packages. And actually, these are the most important things, but at least it's already there. And with that, I would like to thank you, and I'm happy to answer questions in the next 4 minutes.
Thanks very much. So we already have a question here, and I'll ask us to restate the question again for the room and for the camera, please.
Okay, the source and sink nodes model abstraction is brilliant. That has applications in a variety of sectors, including data and vehicle transport. Was that design inspired by one of those other sectors? And conversely, can this package be used to model transport of other things besides energy, like data and vehicles?
So the question was whether source and sink, which is a concept which is frequently used as well in other commodity transport models, and whether the package could be also used for outside energy. Personally speaking, I would say yes. We do not differentiate too much at the time being. We don't work with units yet. It's one of the many points on the list which we want to implement. But for us, for example, CO2 transport is a rather important point. Norway tries to build a business model around that. So the whole system could be used for CO2 transport network design, which then is less energy, or it's not energy, but it's mass. So I don't see any issue why it should not. we're rather agnostic at the time being, but we still have to improve on the units, that we essentially have a bit of a save there and don't require that anything is done a priori but by the user, that it works out.
Maybe one more question, or sure.
I'm not an expert on any of this stuff, but I've also seen packages from the U.S. National Renewable Energy Lab, Power Systems. Is there any relationship between Power Systems and the package you have here?
So the question was that there are also quite a lot of other packages for energy system modeling from NREL, as we've seen before, and with power system analysis, and also natural gas package. No, we decided, or we used quite a lot of concepts which we developed in previous models used at SynTef, but we decided to go from scratch and have the full control over and overview what is happening, and try to make it as simple to use as possible.
Can we all thank the speaker again for a nice talk? I think it's very interesting that there are such a number of different energy system models in JUMP that have all kind of grown up over the few years, and it's kind of interesting to see the different approaches that people are taking.
And if you want to visit Norway, it's beautiful.
So up next we have James Foster from Down Under in Australia. He is also an energy systems modeler, but will not be talking about energy systems modeling in the next half an hour. Instead, James has been working a lot on some of the JUMP documentation, and he's going to kind of take us hopefully on a tour of through the different types of models you can solve in JUMP, and maybe through some of the newer things that we've been adding over the last wee while. So if you've missed anything, maybe now's a good chance to kind of catch up on some more work that we've been doing in JUMP.
Great, thanks for the introduction.
James, take it away.
My fellow Antipodean. So yeah, I'm privileged to be here. I'm James Foster. I work for the Australian CSIRO, which is Australia's national science agency. But I'm here just talking about JUMP and not about my energy system modeling work. Yes, you'll have much to learn about JUMP, so I'm glad you're here. This is a brilliant graphic that I think someone here produced, which is what are we doing when we're doing JUMP, essentially? We're doing a reproducible workflow. And where are we in this workflow? So out of the data process, computing process, and the results and reporting process, we're here, right? We're in the decision model. We're right in the heart of things. And that's what's happening in JUMP. But more simply, if this is the pipeline of what's happening, analytic data in, the algebraic modeling language is where JUMP is, the optimization model, and the solver solution algorithm, solver output. So that's where we are in the computational pipeline. Maybe I don't need to show this, but maybe it's also good for people that aren't so familiar. What is an algebraic modeling language generally? They're domain-specific languages. In this case, obviously, JUMP is an embedded domain-specific language within Julia. And they're descriptive, right? So it's all about describing what you want out of the model rather than being imperative and saying how you should solve the model. And the fun as a modeler is model formulation. And so JUMP gives us the tools to do those interesting things, and we've seen lots of examples. And hopefully, when you write JUMP models, they're readable. They're also reducible, and they have easily maintainable components, as we saw in the last talk. And hopefully, some of the examples here will demonstrate that. Really, just if you don't come from an algebraic modeling background, what are the components? We've got the objective function. We've got sets that organize the model. We've got parameters, which is another word for fixed data that defines the model. And of course, the decision variables are the things that are the unknowns, the unknown variables. And we have constraints and inequalities. And I'm going very fast, but hopefully this serves as a reference point. OK, so just to get us oriented with JUMP, classic knapsack problem. Everyone uses this to get going. So what does it mean? We want to maximize a linear combination of so-called benefits. The CIs are the data of the problem that represent some sort of profit or benefit from a choice. We have a weighted sum that's within some budget B. The weights, WIs, correspond to sort of the weight of the choice which we're making. And we constrain our decision variables to be 0 and 1. And this is, so I'll initially talk about the combinatorial examples in JUMP. So when we say that a variable is in the set 0 or 1, we're saying that an item can either be included or excluded, and there's nothing in between. So do or do not, there is no try when it comes to binary variables. So how does that look when you convert that mathematical formulation into a JUMP problem? So there's a bit of boilerplate, I guess you'd call it. You have to load the package using JUMP. You have to load a solver. Highs is the current favorite for a lot of examples in the documentation at the moment. And of course, we have the data of those profits, those CIs, the weights, the Ws, and the capacity is that budget constraint. And so sometimes when you read a mathematical model, it's a bit backwards. So often we define the variables first and their constraints. So we sort of read it from bottom up. And so that corresponds to the variable declaration, defining our variables. We define the objective using the objective keyword, and we define the constraints using the @constraint keyword. OK, and then we can optimize that and solve. OK, and just in this whole process, how do we find the solutions? Well, that whole process gets us ready to hand off our model to a solver, which is essentially, you can think of it as the solution algorithm. Why is that great? Because we delegate all the responsibility for numerical implementation, precisions, tolerances, and so on to that solver. And the great thing is we can swap out solvers using JUMP. We can also tune our solvers for particular use cases to make them more efficient on particular problem classes. And you can think of the algebraic modeling language as somehow compiling, in a very loose sense, the model down to exactly the data inputs that the solver needs in order to run. But we don't have to worry about that. So this is the magic of algebraic modeling languages. A bunch more stuff about finding solutions. Actually, I'm not going to really go into this. But just to emphasize that if you're not familiar with this, different, more effective solvers can be used if you find that the solver that you're currently using isn't great. Maybe it's better for your problem class. Maybe it's had more development time. For instance, commercial solvers sometimes are much more efficient than other types. OK, so let's do a quick tour of examples in the JUMP docs. You might just think maybe the docs are help you understand some of the syntax. Well, actually, there's a whole bunch of examples in there that I find interesting. Hopefully, you will find interesting, that you'll be inspired after this talk to go have a look at. So I'm going to first divide it into the combinatorial types, and there's some continuous types. There's some more specific applications, and I'm going to talk about recent additions and extensions as well. So this is the classic, in a sense, another classic combinatorial problem, which is the n-queens problem. And I guess I like this. Often people use this as examples when they're demonstrating certain systems. It's really intuitive, I think, and quite simple. As if you imagine if you have a chessboard and you have to place, in this case, 8 by 8 chessboard, the standard one with 8 queens that you need to place on that chessboard, and you have to place them in a way that no queen will attack another queen. So we can write this entire problem quite succinctly in JUMP. The constraint that there is exactly one queen in a given row or column is essentially just a sum constraints. You have to sum these decision variables. You can only choose one of them. So we have 2 of those. And finally, we have two constraint declarations here that within the loop that represent the diagonals as well. So there's a nice correspondence here between the picture and what we're actually doing and the actual lines of code. And really, it's concise, right? It gives you just enough to describe the problem and no more. So I enjoy that. And if you optimize and then ask for the solution, I find that even the layout of the printing in Julia actually looks a bit like a chessboard, and it actually shows you exactly what's happening. And if you notice, in fact, that the solution is not the solution that's presented in the picture, but that's OK. What's happening here is that there's no objective. And if there's no objective, well, even if there is, often you can have equivalent solutions, feasible solutions for the problem that aren't the same thing. And just to plug that, I wrote a blog post that's on the JUMP dev site that actually discusses this And if you're interested in finding out how to access problems that have multiple feasible solutions, particularly in the combinatorial sense, have a look at that. Yep. All right. Of course, Sudoku, who can go past combinatorial problems without demonstrating that they can do Sudoku. So again, I'd just like to sort of say that, again, it's a concise representation of the Sudoku problem. Really, we're describing things as we want, as we sort of think of them intuitively rather than imperatively describing how we go about solving the Sudoku. And in this case, we're quite similar to the n-queens, where we're having constraints that represent rows, row constraints, column constraints, and also we need to represent the sub-cells as well, the 9 by 9 sub-cells. And again, the solution prints nicely. It looks a lot like how you'd represent it. And there are certain things here. There's some logic that we need to involve in this example where if we are given certain cells, right, that we need to enforce the fact that those cells are fixed, those particular entries are fixed, then we can use the fix keyword in JUMP in order to specify any variables that we require to be exactly equal to some given data. Okay, so this is the thing that sort of I didn't know coming from a more classical optimization background is I'm learning some of these things, this approach, because now JUMP has a constraint programming toolkit, which is pretty great. There's these, you might call them primitives of constraint programming that you can now use to be even more concise and representative of the way you might think about the problem. And I won't read these out, but you can see that there's a whole bunch of very useful and interesting constraint programming primitives here. And here's the Sudoku problem again, written in the constraint programming style. And you can see it's even better, right? It's even tighter. I've used a larger font and everything. It fits really nicely. So I recommend having a look at that. I don't come from a constraint programming background, but I'm very impressed by how nicely this represents exactly what you want to think, how you want to think about the problem. But lest I give you the impression that JUMP is all about combinatorial problems. It's not at all. This is a classic, maybe it's not a classic example, but for people who've been around in JUMP for a while, this is the problem that we point to is an excellent example of a continuous problem. There's no binary variables or choices involved here, and we can use JUMP for optimal control problems, and it composes nicely, as Julia does, with plotting and all sorts of interpolations. For instance, we're using this interpolations package in order to work with the data. So that's another brilliant example. And there's this neat page, if you've never heard of semi-definite programming, and I recommend checking this out. There's a bunch of very short and concise examples, some with pictures, that demonstrate what you can do with semi-definite programming. You can do things in statistically related, geometric problems, Loesch numbers related to things like information theory and uncertainty sets. Just to give you a flavor of some of these simple semi-definite programming examples, here's one, sort of this classical problem of embedding a graph metric in a Euclidean space. Essentially asking if you have this particular graph and the distances between the nodes have to respect the distances in the graph. In this case, you're asking for 3 things, all being a distance of 2, so essentially away from each other, as well as a distance of 1 away from the middle node. This is impossible by the sort of triangle inequality, but what you can do is solve an STP that approximates this and embeds the sort of best possible version of this within the Euclidean space. And so very simple and short, again, concise. I would argue formulation of this problem can be written in JUMP. Another fun one is the ellipsoid approximation. If you have point clouds and we're asking to essentially summarize what does this point cloud look like in terms of its, this is synthetic data for this case, but what is it, sort of the geometry of the point cloud? And can we make a best ellipsoid fit rather than a linear fit? we're asking this question. And so we turn this into, again, a semi-definite programming problem. And we use this jump set, which is the PSD cone, positive semi-definite cone. And we can access some of the more obscure, one might argue, sets as well. This is the root det cone square set as well, to easily express this problem. And for instance, it generates this solution where it summarizes a very tight ellipsoid fit around the data. So Julia solved the two-language problem, but JMP solved the dual-language problem. So there's a recent, I'm not sure how recent it is actually, a package dualization thing, well, at least I've become recently aware of it, that is able to work with the dual, help you work with the dual of an optimization problem much more easily. And so here's from the documentation. What does it do? It reformulates problems to meet the input requirements of solver, which can potentially be solving this dual of, in this particular case, conic models. They can be much more efficient than solving the primal. So very quick and rough sort of translation here is it's not always better, but in some case it can be significantly better. So primal variables and constraints, and this would be the dual variables and constraints on a sort of transformed, automatically transformed model. Don't look too closely. The count isn't exact, but it gives you a sense of some of the in some cases, you can get a better, more efficient model as a result. Right, and so what was mentioned in the State of JMP talk, which was this new introduction of complex, you can model directly with complex variables. So there's quite an interesting application that came in through the forum, and it was subsequently written up by Oscar, which is quantum state discrimination. So in quantum theory, as I understand it, just like in PowerFlow, sometimes it's much more convenient to work directly with complex numbers. And in this case, can represent an estimation of quantum state. Don't ask me any more questions about that, using both complex numbers and the complex version of the positive semi-definite cone. And so you can use that all in one to write this optimization model. And something I'm a bit more familiar with, which is as an energy system model, optimal power flow. Here is an entire optimal power flow model written on one slide by using complex numbers directly without projecting the complex variables themselves, in particular voltage variables add into their real and imaginary components. Simple network, I guess it's quite small, but it still serves as an interesting example. And in this, we solve the nonlinear model in this case, and we also transform to a complex semi-definite programming relaxation of this model as well, and solve that with the Clarabelle solver, which is a new addition to the dependencies in the documentation. And yeah, so just moving on to some other examples in the documentation here. There's nested optimization problems. What are nested optimization problems, right? So we have an upper and a lower level problem. So on the one hand, we have, think of the x's as fixed in the lower level problem, and we're asking to solve this z, essentially, based on in this lower level problem. And so that's represented, I haven't written out what the, if you can imagine just writing out that as a constraint, it's just a standard Julia optimization problem. Just write out the constraints and objectives and variables of that. That's inside that lower level function. And then the optimal value of that lower level function then forms essentially a term in the upper level problem. And we need to then solve this entire thing. So there's a very nice detailed walkthrough of how to do those types of problems. And I would be remiss to talk about things that aren't necessarily in the JMP documentation directly, but are extensions that you may or may not be aware of. So the multi-objective optimization now lives in the multi-objective algorithms package, the MOA package. There's a more extensive version of for bi-level optimization problems beyond that simple example in the bi-level JMP. With diffopt to differentiate through and then optimizing over a set of structurally parameterized problems, differentiating through those parameters. Parametric opt interface to efficiently modify parameters in a problem, so key data and constants. Polyjump for polynomials as decision variables. We have Oscar's package, SDDP, for multi-stage stochastic optimization. And one that I think needs more love is piecewise linear opt for modeling problems containing piecewise linear functions. This is the last part of my talk, I guess, which is always pass on what you've learned. So how can you contribute to the documentation? So I'd like to maybe prompt you to contribute to the documentation and bring your experience and share what you have. Do you have an interesting example in your particular area? Can you simplify it in a manner that's useful for a tutorial? Maybe you can translate an article or a book chapter, or maybe you have an example model written in another modeling language that you can translate it through. Maybe you have an idea that demonstrates some of the more so-called obscure sets in JUMP. So power cones, maybe some geometric programming ideas. So why should you do that? Right? So it's great benefit to students, whoever those students are, whether they're just students of the language or otherwise. Maybe it will attract people working in that area, your area, to try JUMP if they can see that they can relate to that example. And in fact, the documentation examples that we have actually help the JUMP code testing, so it helps overall as well. Just to stir your imagination, this is a great book if you haven't. Just get it out of your library, and then there's a whole bunch of chapters here on. These are all the examples of things that. I'm sorry. That was my computer telling me to have a break. All right. How embarrassing. All right. So these are all examples of things that we don't have that don't exist in the documentation yet. So maybe some of these applications would be great to include as documentations. All right. So what else can you do with the JUMP documentation? Well, actually, it's a really good example of generating a Documenter-based GitHub IO site. So if you don't want to use JUMP, just have a look at this, and there's some great examples if you want to generate your own Documenter stuff. Read it, please, and then open an issue and pull requests if there's any feedback you've got or parts that are unclear. Have a look at the one-page JUMP API reference, and then tell Oscar what you think about it, because he's open to changing it. Anything else? This is my wish list. I wish you could have. I put this in, I guess, independently of what we talked about. I've mentioned before in the session. I wish I could do this. So I'm doing this manually at the moment. So here's my tech, and here's my actual sort of the code. I wish I could have tech doc strings that sort of work without me having to manually do that. Thanks. And any questions or rebuttals to what I said, be welcome. Thank you.
Thanks. So we have a couple of minutes for questions, but I have a more logistical announcement. I have been informed that we're taking a photo at 12:30 sharp up on the lawn by the food trucks. So we might just have, say, one question so we all have enough time to get up there in time for the photo. So any questions from the audience? And then, well, if not, then maybe we should.
So actually, for the NQueen problem, you can make it shorter.
Okay.
So even better with so you can assume that it's actually you just need a vector of matrix because you can assign like the indices of each variables as like the x coordinate or the y coordinate. So you can gain even more and have a shorter.
Okay, we'll shorten the NQueen problem. In fact, I enjoy vectorizing optimization problems if possible. So there you go. Please have a look at the documentation. If you find a nice vectorization equivalent, let us know, and put an issue or a PR. And brilliant. Okay, great.
So can I ask that you all join me in thanking James, but all of the speakers in this session. And we will adjourn the JUMP talks for today. So this afternoon there's just the regular Julia talks. And then tomorrow we'll be back, and I think in 155 upstairs at 9 a.m. So we'll see you then.
When I present.
functions. Yeah. Yeah, please.
Hello. Hello. Okay, I think we should be good to go. So our first talk would be from Volker on topological invariants of quantum systems. Please take the stage.
Hello, I'm a graduate student at the Institute of Science and Technology in Austria, and I'll present some results how we use Julia in evaluating this topological invariance. And I hope you're a physicist because this is pretty technical, but if you have questions, of course, about quantum mechanics, you can also ask me. We're interested in the intersection of these areas like topological physics, non-equilibrium, and many-body physics. While I had projects in several intersections, it's difficult to combine all of the stuff. And the main idea is to generate new material properties and eventually improve materials which are, so to say, they're up to now. And in this project, I only combine topological physics and non-equilibrium, which is already pretty difficult. But there are some interesting phenomena. And what is topology? Topology, you can understand it from a physics point of view. Very simple, if you just consider the pendulum of Foucault, that if the Earth was flat and not rotating, there would not be a phase. But if you rotate now the Earth and you have a curved manifold, then there will be a little phase of 2 millimeters each of oscillation. And you can understand this in terms of differential geometry and topology. And it's really interesting, even though it's a very simple phenomena. And in physics, normally what we have is we see these geometric phases, and this just means that if you start in North Pole and then you go south and then you go east and then you go north, then your vector will have rotated. So there's parallel transport because it's a curved manifold. And the same we see in quantum physics. And then there's this phenomenon which looks completely different, but is very much related. So if you have a magnetic field and you have some electrons, they will do this little cyclotron orbits. But on the edge, they cannot complete their orbit, so there will be a flow. And this is very sketchy, the bulk boundary correspondence, which we will also see. And then there are like this topological excitations, vortices, and this kinds of stuff. And yeah, and it's all related essentially to the same phenomenon. And so unfortunately, I cannot go in much detail, but in quantum physics, so to say, all of the stuff, the curvature arises through the Berry connection, which is just the change of the wave function due to some parameter. So here I chose parameter k, but you can do whatever you want. And the Berry curvature, so to say, the curvature on this complex manifold is defined as normally how you would also do it in electrodynamics. And then, for instance, for a 2D material, for some 2D materials, you can calculate the Chern number, and this will just be the integral of this Berry curvature. And here I show you how you can do it in Julia. I mean, it's a very simple calculation. Every grad student who dives into topology knows how to do this. But still, it's very simple in Julia. So you have these little cells, and you basically what you want to know, what is the flux, so to say, this yellow rings, what is the flux through each cell? And you can do this in a parallelized fashion. In this way, I mean, I cannot go into this, but you see it's rather simple, and it looks like this. This is the curvature. And for this model, when we're in the topological regime, you see that there's some finite curvature on this manifold, and this integrates to 1, so there's a Chern number. And from a point of intuition, this just means that there's like a charge inside of the surface, and we are measuring the flux through the surface. So if we're outside, so if we move this ball somewhere else and this little charge is not inside anymore, then the Chern number will be 0. So what is the singularity over there? This is exactly the point where the gap closes of the system. So it's a band system, and this point is really interesting because, I mean, here it's just a point, but for more interesting so to say, examples and models, this is not just a point. And you see that the topological phase transition happens exactly at the point where you, where so to say, the gap closes. So there are 4 different possibilities for the parameters where the gap closes, and this is where you go from being non-topological to becoming topological. So in our models, we look at driven systems, because there you can do other stuff as well. So we just solved the Schrödinger equation on an operator level. And this is already interesting because so we have a system which is driven, so it does not have a fixed energy. The energy is not conserved. But what we can do is we can diagonalize the time translation operator and learn a lot from it and look into the topology of the time translation operator. And in Julia, it looks like this. I mean, this is very simple. You can just plug in an operator into the differential equation package, and it will solve the Schrödinger equation. It doesn't need to be a wave function. It can just be any matrix. So what can we do with this stuff? So here I've shown an example with many stuff that you will not understand, but just sketchy from our own research. So we look at topology of periodically driven molecules, and what you see is that there are these gap closings, then there are these states which are localized, so these are these edge states which I've mentioned before, and there are also there's a topological charge associated with this topological Dirac cones. But now, this is not the only thing you can do. It turns out in the system there's a non-abelian feature. So this, if you have Dirac cones in different bands, they do not commute with each other. They carry some kind of fractional charge, some kind of color charge, so to say. And this is why you have this kind of anionic behavior, and they do not commute. And there's a new topological invariant associated with this model, which is the Euler class. And there's some kind of new Euler connection, which also gives you some rise to some kind of curvature and a topological invariant. And now the question is, how can you find this in a real system? And for this, you need to know where the gap closes. Now it turns out exactly at the point where the gap closes, this gap function, so to say, if you just calculate the difference between the energies, this defines a manifold. So the gap manifold, so where the gap closes, is a manifold, and you can use the implicit function theorem just to continue it. And there are some libraries how to do this, and that's really cool because now in the Julia ecosystem, the mathematicians already did a lot of work, and you can just build on this work, and you don't need to recalculate, so to say, the parallel transport and all of this. You can just use it. And here I have a simple example. If you do not use this, how you could converge just using finite diff to this manifold. And it turns out, I mean, it's for real systems, this can be really complicated. So this is everything which is colored here is where the gap closes. And of course, this is in a real system, it's not as easy as you would do in a toy model, and there are many knots and braidings and stuff like this. But if you search, you can also find beautiful, so to say, knots, and this is exactly what we wanted to find. This is exactly where, so to say, you have this Euler invariant, and you can also see it in the wave function that there are these Dirac cones, and the Dirac cones, they have Dirac strings in between, and you can see them in the wave function. And these are strings which you cannot remove, and they go through each other, so there are different Dirac strings associated with different Dirac cones, and they form something like a knot. Yeah, and that's basically it. That's what I wanted to say, that you can use this nice ecosystem to do very complicated stuff. And yeah, by the way, that's in Vienna, if you have not seen it. It's a beautiful city. And yeah, we can do this quasi-energy business, and we can use these nice packages. And yeah, I'm open for questions. Thank you.
Thank you. Really fascinating how much you can do with fairly straightforward Julia. Any one quick question?
Yeah, thanks for the great talk. So I have a question about bifurcation, so bifurcation toolkit. I'm just curious, like how you use it in this specific context. Maybe you can say a few words about that.
Yeah. So if you have a differential equation, so say dynamics. If you have a dynamical system, it's very straightforward to use it because then you can just calculate where your system has a bifurcation. But if you, so to say, start with a different thing, you start with a manifold, the flow on this manifold will define your differential equation. So this is already the first difference, you need to use this implicit function theorem to define your differential equations, and then you can use it, which is not super easy. This is why I used all kinds of packages and saw what works best. I mean, in the end, I used this very naive approach, but I mean, this is work in progress. So I think that they have really fascinating ways, if you're at a branching point, how to classify it. So that's where I would use it, like if you have a Hopf bifurcation or something. Yeah.
Thank you. Let's thank the speaker once more. And we are heading to the second talk in this session, a toolbox for quantum many-body problems.
Okay, so hello everyone. My name is Tao Wang. I'm a PhD student in UMass Amherst. And so it's my pleasure to introduce you the GreenFunc package we developed, which is a powerful tool for solving complex quantum many-body problems. And this work is done in collaboration with Kun Chen, Pengcheng Hou, Xiansheng Cai, and Zhiyi Li. So in the most general sense, so a Green's function describes a response at the coordinate x2 and time t2 with respect to a source at x1 and t1. And so a typical example would be the sound wave shown here. And so in the many-body physics context, this would correspond to creating a particle at x1, t1 and detecting the particle at x2, t2. And so almost all experimental observables are Green's functions. And so several properties of the Green's functions make it numerically challenging to handle. So the first one would be the multidimensionality. This is because we can have n particles involved in the process, which creates multiple sources and responses. And so the second property is singular analytical structure, which basically originates from long-range correlation either in space or time. And typical example is a Coulomb interaction. So since Green's function is a single value function on space-time variables, so it's natural to save it as an array on discretized meshes. And so this leads to the core structure in our package, which is the mesh array shown here. And of course, to overcome the challenges I mentioned before, we still need to use efficient meshes that's specialized for different purposes. And this is generated by 3 other packages we developed, shown in the right column. So the first package is the composite grids. So the idea behind this package is that typically physics behaves differently at different length scales. For example, here we can have water molecule droplets and waves. And so this leads to also multi-scale behavior Green's functions. As an example, here we have a Green's function which is mostly flat, but it's exponentially sharp at the around point 1. And so to capture this behavior, so we use composite grids, which is basically panels divided into subgrids. And so here we have the first layer as a panel logarithmically dense at point 1, and which is showing the blue box. And then in each panel, we have a quadruple subgrid, which is a barycentric grid that enables the high accuracy interpolation. And so for more complex Green's function, you can always use a nested structure by replacing the subgrids with a composite grid. And so here is an example code for generating the Green's function shown here. And the second package is the Brilliant Zone meshes. So this is developed for Crystal, So most solids in our nature are crystals with lattice structure that has discrete translational and point group symmetry. And so due to the translational symmetry, one can just consider the unit cell, which is, for example, in this triangular lattice shown as the hexagonal. So one special type of the unit cell is the Wigner-Seed cell, which has the same point group symmetry. And in momentum space, that would just be the Brillouin zone. And so one can further reduce the calculation to just the irreducible wedge of the Brillouin zone by making use of the point group symmetry. That would be the red triangular shown here. And so in 3D, that would be a significant reduce since the fraction would be much smaller. And so here is an example of the 3D irreducible wedge generated by our package. And so this would be an example code. So of course, we also equip the Brillouin zone with a meshes shown as the yellow points here. And so the third package is specially developed for Green's function. So as one can see in this figure, so the Green's function in the imaginary time space typically has very singular behaviors. However, it is proven that one can make use of the universal structure, so-called lemma representation, to identify a discrete set of grid points, which can be used to reconstruct the whole Green's function up to any given accuracy epsilon. And these grid points are universal in the sense that for a given epsilon, it only depends on whether you have fermion or boson. And so this is called the discrete lemma representation, or in short term, DLR. And so for a given temperature T and epsilon, the number of grid points required is scales as log 1 over T and log times log 1 over epsilon, which is typically just hundreds of points when you have very low temperature at 10 to minus 4 Fermi temperature and very high accuracy at 10 to minus 10. And so the package also enables very fast and accurate Fourier transform and interpolation, which outperforms the standard uniform grids with the fast Fourier transform. And so here we show a example of our interface for performing the Fourier transform and interpolation. And so with all the packages we developed, we were able to study two outstanding physics models with unprecedented accuracy and efficiency. So the first one is the so-called SYK model, which was first proposed as a as spins with all-to-all random couplings. And this is both related to condensed matter physics, such as strange metal and high temperature superconductivity. And it's also connected to black hole physics by the so-called holographic principle. So before this was typically by conventional method can only be solved down to like 10 to minus 2J. However, with our package, we were able to solve the whole problem with just this one page of code down to 10 to minus 14. And so these are basically the, for the experts, the diagrams that we need to solve. And the next problem is the ultra low temperature superconductivity. So basically, many superconductors in nature has extremely low temperatures, such as this nice picture with bismuth in from Wikipedia, and so it can be as low as 0.0 millikelvin. And so it would be extremely hard to resolve with conventional numerical method due to the high computational costs. However, so with our packages, we were able to extract the superconducting phase diagram for the uniform electron gas with the lowest transitional TC as 10 to minus 200 Kelvin. And so finally, I would like to advertise that all the packages were developed under the numerical effective field theory, and which we have the ultimate goal of developing the quantum field theory for electronic structures. And so please feel free to ask any questions and also explore our packages and submit any issues to our. Thanks.
We're running out of the 10 minutes, so we need to jump to the next speaker, but please don't hesitate to engage with all the presenters during the various breaks. And I'm actually next, and Volker was gracious enough to help with timing. Okay, so hey everyone, my name is Stefan Krastanov. I'm also from University of Massachusetts at Amherst, and I'll be discussing some tools we're building for simulating entanglement distillation circuits. So first, let's start with a quick introduction to the context we're talking about. So I won't go too in-depth on the quantum mechanics here, but say we have two entities, Alice and Bob. Each one of them has a qubit, a degree of freedom that can support quantum superposition, and those 2 degrees of freedom that they have, those non-local degrees of freedom, they're in some entangled correlated state. And frequently it's convenient to represent the basis of possible entangled states as these A, B, C, D states. We'll be mostly focused on this first one, the state where they are perfectly correlated to either be both 0 or both 1, those 2 qubits. But due to noise, some other state might have been generated, one of the other 3. And for some background on that topic, there was a nice art installation at the Yale Quantum Institute that I helped set up a few years ago. That's a great introduction. If you're new to the field, you can jump on that. We made a whole sculpture representing a dilution refrigerator with qubits in it. Okay, so the problem is that these qubits can be noisy. Instead of preparing the desired entangled state 0, 0 plus 1, 1, this perfect superposition, due to, say, a bit flip, the qubit, one of the qubits might be flipped, and actually the correlated state you end up with is 0, 1 plus 1, 0. So the goal of entanglement purification circuits or protocols is to guard against this type of errors. So what we usually do is we set up an entanglement distillation or purification circuit in which we have a number of entangled pairs, and we use some of the entangled pairs, sacrifice them in order to try to detect the errors in the other pair. So for instance, here we have Alice and Bob sharing 2 pairs now. This is the first pair, and this is the second pair. And Alice and Bob are basically doing the same circuit, where they use a CNOT gate between their half pairs in order to then transfer errors that might be detectable by doing a coincidence measurement, sacrificing one of the pairs. And then if through that sacrifice they have not detected an error, they have higher certainty that the preserved pair, this leftover pair, is actually pure high-quality A pair. So one way to think about this is as errors propagating through a circuit. So here I'm plotting the half circuits of that Bob is running, Alice is running the mirror image of that circuit, and say that there's an X error. This gate that we're having here propagates that X error from the pair to be preserved to the sacrificial detector pair. And that way, by propagating these errors, you get to use one pair in order to detect errors on the other pair without having to perform non-local measurements. That's the difficulty here, that these are entangled states. You cannot just bring the two qubits together and check them for errors. That's why we're sacrificing that other pair. A more abstract but useful way to think of these entanglement distillation circuits is as permutations over the Bell basis. So here we have the 4 Bell states, but we have 2 pairs, so we have 4 times 4, 16 different possible states. And this circuit that we have here before the measurements, it basically performs this permutation of the Bell basis. It moves the state of pure, correct, no error, to again, the state of pure. Nothing interesting happens if you don't have any errors. But it, for all the other states, it permutes them. If there is an error on one of the pairs, that error might be moved to the other pair. And that, again, is the technique you use to do detection. So our state would be some probability distribution over this basis of 2 Bell pairs. Our circuit will permute the basis, and now we'll have different probabilities assigned to different states. And our coincidence measurement, for instance, a coincidence measurement on the z-axis, will select only for A or D states on the sacrificial pair. Basically, it would cut half of the probabilities, and the hope is that the half of the probabilities that are left, when renormalized, they lead to higher relative probability of having a pure, correct state. More pictorially, here is the hypercube of possible states of 3 pairs. So here, each axis corresponds to a state of one of the 3 pairs that we have. And the desired state is this here in the corner in green. But if we have one error happening on any one of these pairs, we have this, these blue states. And then if we have 2 errors, we have these orange states. If we have 3 errors, we have these red states. And thankfully, the chance for having no error is higher than the chance for having an error. So let's scale them. The size of each cube corresponds to the relative probability to have that state. What we're doing with the CNOT gate is we're performing this permutation. And then when we perform the measurement, what we're doing is we're deleting these 2 columns. And now the relative weight of the green with respect to the rest is higher. The thing is, we need tools to model this more efficiently. Most of the tools we have use something called Clifford circuit simulators, but actually in this context, we can do much faster even than that. With Clifford states, you might know this. This is a typical technique for modeling error detection circuits. And the A state is denoted by the 2 observables for which that vector is an eigenvector with eigenvalues +1. And we have similar observables for all the other states. But notice that for the tensor product of a bunch of Bell pairs, the tableau representing these observables is actually block diagonal. Not only block diagonal, but these blocks are always the same. So actually, all you need to track is these phases. So instead of using an exponential large vector or a quadratic large tableau, you can just use this vector of binary numbers phases. So typically for n pairs, the naive way with state vector representation is exponentially expensive, the tableau is quadratically expensive, and our trick gives us a linearly expensive data structure. Then you can also represent all possible gates that actually preserve that structure. All possible gates that you care about if all you care about is purification. Those are not general enough to represent other types of quantum computation, but they are general enough to represent any type of entanglement distillation circuit. In our paper, we describe exactly why the gates look like this. The important part is that you have some poly degrees of freedom, you have some single Cliffords involved, and you have a number of very particular 2-qubit Cliffords involved in the permitted gates. And those 11,000 or so gates, they can be modeled extremely fast using our formalism. Actually, if you compare it to other state-of-the-art techniques, well, here what we're doing is that for a number of Bell pairs, up to 1,000, we'll be performing that simple purification circuit, the 2 CNOT gates. And we'll be measuring how long it took to just do a pair of CNOT gates and nothing more on one couple of bell pairs. The dense and sparse formalisms with state vector tableaus are obviously exponentially expensive. They're not something you'll do if you have more than 10 bell pairs. The Clifford formalism, which is a well-known formalism for error detection circuits, is not too bad. But our technique is orders of magnitude faster, and it's fixed cost. So it permits us to model really large, intricate circuits and optimize over them. And in our paper, we actually describe some of these optimization results as well, and we provide distillation circuits that are far outperforming anything else available in the literature. Here, the BP Gates is the underlying simulator, and if you're interested in that type of work, please apply to UMass Amherst. And that's all I have. I think we have enough time for a very quick question. And if there are no questions, I'll be around. Of course, I'm open for discussions. But then let's jump to the next speaker. I think that's Michael Herbst. Yep, great. Thank you.
All right. So thanks for all of you to be here. So my name is Michael Herbst, as you might know, and I'm from EPFL. And this is Paul. Paul is from the University of Aachen, where I basically did my postdoc. And Paul basically is the master student that I supervised. And essentially today we are presenting Paul's work, mostly. I mean, I helped a bit, but it was mostly him. I really should say that. All right, so we're going to talk about surrogatizing quantum spin systems, in particular using reduced basis methods. I will explain what both of these things are. But before we go into the details, I think even though we have a pretty wide audience, it would be quite nice to give a little bit of a general motivation for quantum, right? So why do we care about quantum effects? And I mean, I just make this proclamative statement here, quantum effects are everywhere. So in particular, what I'm talking about is like if you want to understand how solar cells work, if you want to understand how batteries work, microchips, all these things. I mean, quantum computers is a lot what we heard about in the previous talk. There was a whole quantum session, as you might know, at JuliaCon, right? If you want to understand new materials, basically come up with new solutions to the problems that we have in the 21st century. This is where quantum effects really play a role, because nowadays you have to understand when we talk about renewable energies, we talk about, for example, finding new materials for quantum computers. In the end, we really need to, we're fundamentally limited by the materials that we have at hand to solve these problems, okay? So therefore, really coming up with fundamentally ways to understand quantum effects and, therefore understanding basically the basics of physics gives us new techniques for finding these materials and therefore making a step forward with the challenges that we have as a society today. And I think one point, just to make this extra clear, is that some of the supercomputing systems I know, about 50% of the computational time is spent just for quantum chemistry simulation. On top of that comes a fair share for quantum physics as well, right? So this sort of stuff that we will be talking about today, that also the other speakers of the session have been talking about, this is really something that happens and, happens to a large fraction. Okay? So, now a little bit more closely to the subject of our talk, quantum spin models, right? So why should you care about quantum spin systems? So in the end, these are really I mean, I would say real models, right? So the idea is you talk about small spins that are arranged in certain lattices, for example. So these are real systems you can manufacture. So there's experimental techniques to really arrange spins on a particular, in a particular order. And as we will see in the next slide, there's a number of parameters that you can really experimentally tune. And the point is really that, therefore, these systems are small, they're simple, sometimes you have analytical solutions, but at the same time, you can really probe it. So it's an ideal way for like an analogous system, if you so wish, to make the connection between physics and experiment, like theory and experiment, and understand how you can model new theoretical problems in an efficient way, for example. Okay, so I really like this idea that, in fact, a lot of these quantum spin systems also reflect more complicated systems. Essentially, they are a condensed form of quantum effects that you can also have in real materials, like in materials that we want to synthesize and use today. So therefore, it makes this nice bridge between something which is simple enough that theory and experiment can directly access it, but complicated enough that we can really study computational phenomena, quantum phenomena, which we don't understand yet. Okay, so one thing in particular that we want to focus on is something known as quantum phase diagrams. Don't look at all the details in the slide too much. It's just basically to give you a little bit of an idea. So the point is that in this particular setup, it's a so-called Rydberg chain. In this chain, we have a number of atoms which are arranged, in a chain. Okay, so far so easy. And the idea is that these atoms have two states, two basically eigenstates, and they can interact in a particular way. So the details I don't want to explain here. The point is only that the laser field that you use to set this up and the interaction strengths and so on, these are all parameters of your setup, okay? And essentially, depending on how these parameters are chosen, you get certain ordering patterns, as it's known, right? So here you see that sometimes all the atoms are green, which is supposed to say they are in the ground state. Sometimes you have some patterns that arise. And this is essentially the trick, right? You have certain so-called phases in which one of these patterns essentially are the dominating pattern. And understanding which parameters to choose to get these phases is something which is of interest to understand quantum physics. And Hamiltonian then pretty much looks like this. So it's a big object with many parameters. And what we are in particular interested in are the eigenstates, right? So the eigenstates of this complicated object for each of the parameters. Okay, so basically for each of these parameters in this two-dimensional space, we want to understand the respective eigenstates. Now, if we really want to do it, we are faced with a big problem. And the problem is that the dimensionality of the Hamiltonian is exponentially scaling with L, which is here, for example, the size of this chain. Which means that if we really want to do this at every parameter point, like we want to find this ground state, for example, this state at every parameters point, this is really expensive. So typically this takes like a few hours to compute such a ground state exactly, or approximately really. And what we want to do in this work in particular is to exploit that, if you are at two close by parameter points, the states typically don't change that much, meaning that they are not linearly independent. So we want to use this to avoid the need to really compute this at every parameter point. And this leads quite naturally to the so-called reduced basis methods. And what we discuss in the talk today is really how you can combine reduced basis methods that I'll describe in the next slides with matrix product states, one standard technique to obtain such ground states. Okay, so why do we believe is there this potential for the reduced basis methods? Well, basically, as I said, the idea is that the states are similar across a phase when you vary the parameter only slightly. So if we basically use very carefully selected points, only a small number of them, where we evaluate it, this should give us enough information to sort of interpolate everything, okay? And I mean, these type of reduced basis ideas have already been explored extremely successfully in the context of PDEs. So, and I mean also in nuclear physics. So the idea is, can't we use it here as well? And just sort of one idea why this should work so we tried this, and it turns out, for example, if you look at the singular value decay, meaning like the similarity measured to an extent between the different eigenstates that you find at the various parameter points, you find to get a certain accuracy, the sort of number of points that you really need to keep scales much less than the full dimensionality of the Hilbert space. And here you see, for example, the decay of the singular values. Right? So this is just from a mathematical point of view an indicator that this should work. Okay? So if you don't understand this, it's not really too much of a problem. The point is this really tells us there's something to be gained. Okay, so how does this work? What do we actually do? Basically, there's two stages, the so-called offline stage where we put in all the effort, so we solve really this full problem at a certain carefully selected number of points, and then the so-called online stage where we basically have the solution and just use it. So in the offline stage, for example, here we have a grid, like a small grid of parameter points that we give to our algorithm, and iteratively, basically, the algorithm selects one point at a time to add to this reduced basis. So in the end, we don't do all the computations, only a selected number of points. And essentially, we follow the so-called greedy strategy, which means that we have an error estimate that I will briefly discuss on the next slide. And this error estimate, we just evaluate at every parameter point, and then we find those points where the error is largest. And these are the ones where we really go into the effort to solve with DMRG or MPS ansatz our full problem. And we only do this at a small number of states. So instead of something like 100 to 1,000, we only need to do something like in the order of 10. Or maybe sometimes 40 or something, right? But not 1,000, that's the point. And once we have done this, once we have built our reduced basis, this is now our approximation for all the ground states. So basically whatever value of the parameter point you want, we use this ansatz with the states that we have actually computed to evaluate independently of the size of the Hilbert space at every parameter point, a quantity of interest. Okay, so one more slide to just make this more clear. So how is really the next parameter point selected? So given that we have already n points, the n plus first point is really selected by this greedy condition. So where this error estimate here is the largest in all the points that we consider. And for the error estimate, we just take the residual for the eigenproblem. And this is, it's a bit surprising, but it turns out you can actually evaluate this independent of the size, like at the scaling independent of the size of the Hilbert space, which means that evaluating this at every point in your testing grid is actually cheap. So the only expensive thing is once you have decided which next point you add to your reduced basis to really solve the full problem. That's the only expensive step in this. Okay, so I'm going to skip this for time. The point is, if we now have such a reduced basis available, then once we know this approximate basis, in the online stage, we can just use it. So now we can, for example, use it to express any observable that we are interested in, and essentially, like by use of this reduced basis, these snapshots that we have obtained essentially recover the information, at any parameter point that we desire. And indeed, the point is again, this is independent of the size of the Hilbert space in terms of the computational complexity. Okay, so before I hand over to Paul, now. Like, what is the sort of requirements for a method that actually computes the exact ground state? Well, I already mentioned that we are doing this with DMRG, but we also use the standard exact diagonalization techniques. So what is required is really you need to be able to compute overlaps efficiently between the states at different parameter points, and you need to be able to compute matrix elements like this, which means that if you think about DMRG, the typical thing to MPS overlaps is doable. MPS MPO contractions is what falls in here. That's also doable. And what is also necessary, because this is sort of an approximation on top of the approximation that you're using for the ground states, you need to be able to somehow control the accuracy of the ground state solver. Okay, so for ED, that's of course just the threshold that you're using for your tolerance, for your diagonalization. And for MPS, this is the standard things like bond order or whatever tolerance you have for your alternating least squares. All right, so that comes to the end. And from my point, and I hand over to Paul for giving you some ideas about MPS and the results.
All right, so also hello from my side. I guess before we go into the results, what this reduced basis stuff can actually produce in practice,
I guess we quickly rehash again something we also probably saw yesterday. So what are matrix product states? So everybody knows what we're talking about. So matrix product states are a way to parameterize basically many-body states by taking linear combinations of many-body configurations, and you have coefficients which you express as products of matrices. And you also have this diagrammatic representation on the right, which we also saw yesterday, so I won't go into much detail. But basically, it's a way of writing many-body states. And you could ask, okay, why would you want to do this? Because it initially seems more complicated. And the reason is that you can basically control this problem that you have, that the Hilbert space becomes really high-dimensional, by basically low-rank approximating these matrices you have in your state. So you make a low-rank approximation of them. And this ansatz is particularly effective for one-dimensional system in the sense what Michael already talked about. You have one-dimensional lattice of particles. And this has to do with the underlying entanglement structure of one-dimensional ground states. And in practice, what this means is that this enables us to basically study larger systems, which translates to more physically realistic scenarios, or interesting scenarios. And so the last thing we need to know is what is DMRG, and that's basically just in our context way to obtain a ground state in MPS format. And just to give you a small detail, it's just by basically iteratively optimizing these matrices towards the ground state as to minimize the ground state energy over the MPS manifold. Anyway, just quick recap on MPS. Okay, so in order to see what this method can do, we need to look at some kind of physical system, and we look at quantum spin models, and in particular quantum spin chains, so one-dimensional models. And what we have here is the so-called Haldane chain with spin 1 particles, and we have two types of anisotropic terms. So we have two parameters D and E, and maybe in this context, it's just important to know that we use it as a benchmark system. The phase diagram is already known from previous DMRG studies, and it looks something like this. So we have these Néel-ordered phases, which is basically anti-pragmatic ordering, and we have a Haldane phase. But what that physically corresponds to, I guess, it's a bit out of the scope for this talk. But let's see what the greedy method, this reduced basis method, actually does. So we take this Hamiltonian, plug it into our method, and what we first look at is what parameter points are actually selected. So again, remember we have this greedy algorithm that kind of selects iteratively parameter point after parameter point and then extracts a snapshot, so solves the stationary many-body problem. And these dots on the phase diagram indicate which parameter points were selected. And what we already can see is that basically in the Haldane phase and also across phase boundaries, we tend to sample more densely. And this is kind of interesting because it seems that this greedy algorithm already understands something about the underlying physics of the Hamiltonian. And so yeah, that's the first thing. And then we can also plot on top of that the residual, which is this kind of error estimator which evaluates how good the reduced basis performs. And it looks something like this. So we get these nice wave-shape like patterns. And what we can also see is that close to the snapshots, we get these areas where the residual is low. So basically that corresponds to parts in the phase diagram which this reduced basis model emulates particularly well. Okay, another interesting aspect about this is that now that we have an implementation using MPS, we can go to slightly larger, like very much larger system sizes with exact diagonalization techniques. And what we look at here is that we want to know how does this reduced basis space actually grow as we increase the system size of our spin chain. And in the case of the Haldane chain, we basically look at, we assemble reduced basis for different system sizes, and then we look at how this residual decays. And I guess unsurprisingly, for larger system sizes, the decay rate decreases. So we basically need more snapshots to reach the same level of accuracy. But the cool thing is that here, what we see on the right-hand plot, if we rescale the axis by L to the power of 0.8, and of all these curves collapse onto each other, approximately. And what this means is that basically at fixed residual or fixed accuracy in that sense, this reduced basis space kind of the dimension grows sublinearly, as opposed to the exponential Hilbert space. And that's already quite remarkable, I would say. So we really have like an effective low-dimensional space available. And what we conclude from that is that basically, as we go to the thermodynamic limit, as in we go to infinite system size, we do need infinitely many snapshots kind of to construct a basis. However, due to the sublinear scaling, we could still reach fairly large system sizes, approaching the thermodynamic limit. Okay, next we want to actually see, does our method produce reasonable physical results? So we look at observables, and in particular correlation functions. And so what we see here is, for those that don't know what that is, basically we take second order moments of this ground state ordering, and basically by looking at, if 2 points on this ground state are correlated, we can kind of detect different types of orderings, which Michael already kind of showed in the beginning, that there's kind of different ordering patterns. And so here in this leftmost panel, we see basically that, if we measure this SZ operator at 2 points on the spin chain, we kind of get a finite signal in this one phase and is black everywhere else. So we have like this order parameter that really indicates that, we have like a certain type of ordering in this phase. And the thing is that it does correspond to, the previous results from, previous high accuracy studies. And I guess this is also true for all the other observables that we measure here. So for example, if we measure spin operators in y direction, we kind of detect this y-nail phase, and then there are quadrupolar operators, and also on the right side we have string order parameters that detect the Haldane phase, but I guess that's detailed physics, which is not relevant here. But the bottom line is that, in this case, in this benchmark model, the reduced basis method produces, fairly accurate and correct results. Okay, as a quick preview, we also study a bit more complicated systems, and in particular this bilinear biquadratic chain, which kind of is an extension of the previous chain, so it's still spin 1. And this has also been studied quite extensively using DMRG and also analytic approaches. And the phase diagram is fairly complex, and I also don't want to go in detail here. But what we found is that being able to basically scan large parameter domains and resolve the physics is actually quite useful to explore parameter spaces, in particular when there's like unknown features. And what we found here, even though this has been studied before quite a bit, is that in one phase, which is also kind of indicated by this clustering of snapshot points, there's like this so-called incommensurate phase, which was previously overlooked. So, this approach is really useful kind of for exploring phase diagrams. But yeah, I won't go into further detail here. Okay, then let's talk about the code side of things. So we coded up this package called reducebasis.jl, and it comes at no surprise that this is written entirely in Julia. And for all the matrix product states in DMRG functionality, we use the itangles package, which I guess many of you are very familiar with. And so the idea is that we implement reduced basis methods for parameterized eigenvalue problems. So as opposed, I guess, to parameterized differential equations. So this is only parameterized eigenvalue problems. And in particular, we have a focus on quantum spin systems, so many-body Hamiltonians. However, it's quite customizable, I would say. So we can use different solving methods, right? So we can use some type of iterative eigensolver, so exact diagonalization in physics terms, or we can use tensor network methods from itensors, but we can also implement custom solvers quite nicely. Then we also have custom error estimators, so we're not only restricted to this kind of residual, and also more technical stuff like orthonormalization techniques, grid types, and also the assembly strategy. And if you want to have a look, we have the code base on GitHub. And yeah, so the question is, why is Julia like well suited for this project? What does it bring to the table? And maybe the first point I want to make is that it's kind of cool, this project, that is Julia was really suitable like for the multidisciplinary aspect. So it started out with Michael and Benjamin Stamm, who is a professor in numerical analysis and also collaborator here. coding this up. And even though I think Benjamin didn't really have previous Julia knowledge, he was still able to contribute. And then I picked it up, and I'm just a master student, and I also didn't really have previous Julia knowledge. And then even in the end, Stefan Wessel, who is a physics professor and also collaborator here, and my supervisor, he even contributed to the documentation, even though he had also not written any Julia. So we had this process of gradual improvement from people across disciplines, and I guess different aspects of Julia make it really accessible and easy to contribute. So yeah, that's the first cool thing about it. And then I would also say Julia is a highly productive language, so we were able to prototype this pretty fast. So I guess we had the first functional version after a few weeks, and even though I was a beginner, I would say. So yeah, that's also quite cool. And I guess this point everybody makes is that this generic type system and composability of Julia is just amazing. And in particular, in our case, it made customizing the code quite easy. And in particular, the generic mathematical structure that this reduced basis theory has translates very well into generic Julia code, with generic types, right? And to make this more concrete, I have this quick example, the simple example. So basically, at the center of this reduced basis stuff, we have an assemble method, and this assemble method takes different types of things, but mostly the most important things are does take a Hamiltonian on which we assemble a reduced basis, some type of grid, some type of information about the greedy assembly, and a solving method and some technical stuff, which is not important here, but solving method as an iterative solver or DMRG or whatever. And the thing is, it basically all calls the same generic method, which is pretty close to the pseudocode, which you write down in a numerical math paper. And however, then when you go further down the line, there are solver-dependent subroutines, and these then call specialized methods via multiple dispatch. I guess this is a pattern which frequently comes up in Julia code. So for example, whenever we compute these reductions to reduced basis space, which frequently comes up, what can happen is that this translates to actual matrix multiplications if it's a matrix made out of numbers, but it can also come down to MPO and MPS constructions if H is an MPO. So, this boils down to different methods. Right. Okay, this brings us to the conclusions. Okay, so this method, this reduced basis approach, is really, really nice to kind of explore and efficiently capture phase diagrams. It's quite cheap actually. It's kind of difficult to quantify reasonably, but if you compare directly against let's say only using DMRG, you kind of gain a few orders of magnitude and kind of speed up if you just use this for scanning phase diagrams for quantum spin systems, but this probably also extends to more quantum many-body systems. And in particular, by using matrix product states in DMRG, we were able to do this for larger systems as previously possible. And what's also kind of cool is that we basically, these surrogate models, these reduced basis models, are mathematically justified in the sense that we build on top of mathematical theory that's been around for quite a while. And we have error estimates and so on. And so one could also imagine that we could build from this an automated parameter space exploration for basically Hamiltonians that we where the kind of phase diagrams are known. And of course, you can also simply integrate your favorite solver of your choice. So the obvious choice would be try to plug in other kinds of tensor networks. Tree tensor networks would be relatively easy because you can track them exactly and so on. But you could also use GPU-based solvers or quantum Monte Carlo solvers in some cases. And again, we have the code base on GitHub. And if you want more info on also the physical details, you can check out our preprint on arXiv. And lastly, we come to the acknowledgements. So our collaborators, Stefan Wessel, Matteo Rizzi, and Benjamin Stamm. A lot of thanks to them. Also from my side, special thanks to Stefan for actually making it possible for me to come here. And I think that's the point where I hand over to Michael again for some advertisements.
Yeah, because I'm also in the fortunate position that I recently got a junior faculty, and basically, if you're interested in these kind of things, please let me know. I have some postdoc and some PhD positions, and with that, we look forward to your questions. Thank you very much.
Thank you. Let's open up to questions.
So could I think about this reduced spaces like a perturbation theory in the states which I already found, so to say, in the surroundings?
Interpolation, rather. You can actually do perturbation theory on top. We haven't done that yet, but that is actually something that comes on top. Yeah, it's more an interpolation between what you have. Yeah.
So in that case, if you go across a phase boundary, it probably doesn't make sense to use the reduced spaces from the other phase, right?
Yeah, well, the funny thing is with this residual error, the reduced spaces will notice that there's a new phase and will do a computation there. So it actually has a state in both phases. And so we'll sort of use the left-hand side state to extrapolate from the left and the right-hand side state to extrapolate from the right. So here you see, Paul, you should explain this. It's your plot.
I mean, I can also explain this. So basically what you can see here is, maybe this is a bit too much at once, but what you basically see is that around each point you solve, kind of the most dominant area where this particular ground state kind of dominates the surrogate ground state you construct is, is built like these Voronoi cells. And what you can, I guess, see across phase boundaries is that you basically have cells that kind of split at the phase boundaries. So you kind of write that across phase transitions, you need ground states at both points to correctly resolve it. So in that sense, you're right. But I mean, the cool thing is that this greedy technique, which selects the parameter points, tends to pick up on that. I mean, there's no guarantee, but it tends to pick up on that there's a strong variation across phase boundaries. So it tends to sample both sides, and then you can kind of interpolate between it.
Okay, cool. We have time for one very quick question and answer. If not, let's take the speakers again.
So, is this working? Yes, I think so. So, it's a great pleasure to be here. I'm Leticia. I'm a first-year PhD student at Carnegie Mellon University in Pittsburgh, Pennsylvania. And today I will be talking about solving the Schrödinger equation with Julia. So first, announcement. If you want to find me or talk to me, you can find me on Julia Slack. You can go to my GitHub to check the codes for my work and my independent track of research with Julia. And you can also open issues, suggestions on my GitHub or find me on Slack. I'm always happy to chat. So what is the Schrödinger equation? It's in the title of my talk, but I didn't explain yet. So let's start from the beginning. The Schrödinger equation, from a formal definition, describes the behavior of a particle in a force field, or it can also describe the behavior of a system over time. And it's based on the idea of taking a physical quantity out of the wave function. And in this case, we are taking the energy out of the wave function by operating a Hamiltonian. And I will explain each element of this equation during this talk. And why is it important to know the energy of a system or a molecular system? Because this equation seems to be simple, but it's very powerful. And over the years, many researchers, chemists, physicists did research on this field and tried to understand and come with methods to solve that equation. And of course, Erwin Schrödinger, Werner Heisenberg, Paul Dirac, and Oppenheimer. So this is not supposed to be an advertisement to the movie, but if this guy did research on quantum chemistry and on the Schrödinger equation and he has a movie, it might be something important. But putting the joke aside and talking about more serious stuff, and I will give a reference to Michael talks, because from the Schrödinger equation and from the wave function, you can extract a lot of information useful for biology, physics, life sciences in general. If you take a look at this first paper, you can see that the density functional theory, one of the methods used to solve the Schrödinger equation, was very important to find and explore new drug candidates for the COVID-19 pandemics. If you take a look at the second paper, you can see how DFT and the Schrödinger equation is important to find new materials. And if you take a look at the third one, you'll see that the Schrödinger equation is important for all life sciences, biology, physics, and chemistry. Now, let's go back to the formalism itself. The equation seems to be, okay, simple, short. You have an operator, you have the wave function represented as psi, and this wave function is an eigenfunction, and you have the energy that you get away from it as your eigenvalue. And if you operate your Hamiltonian to the wave function, you obtain the property. And this is an eigenvalue problem because we were trying to find the energy element in this equation. So the operator and the wave function depend and are modeled based on the system you are working with. So depending on your molecular system, you will have different Hamiltonians and wave functions. So after all this explanation and after understanding that you can take information useful for physics, biology, material science, you understand that quantum chemistry is all you need for scientific discovery. So from that, we can expand the Hamiltonian and the operator in the Schrödinger equation, and we split the Hamiltonian into two different operators, the potential energy and the kinetic energy of the system. And if we write down the expressions for each of these operators, we will find the expanded Hamiltonian for the hydrogen ionic system, for a very simple and small system. We can split up the kinetic energy and the attraction between the nuclei of an atom and the electron that have different charges in a one electron term in the Hamiltonian. And the repulsion between two electrons that have the same charge, you can compute at the two electrons term. And this is important to distinguish because it's easier to compute the one electron terms than the two electron terms, because you need to expand over all the electrons in the system, so you increase your complexity in the integrals. And I will talk about the integrals later. So from this, let's take a look at what happens if we calculate this Hamiltonian and solve the Schrödinger equation for an hydrogen atom, the smallest atom in the whole periodic table. I formed the 8H2 molecule, and I calculated the potential energy surface for this molecule, and you can see how this elements in the Hamiltonian change. I didn't decompose them, but from the potential energy surface, it's easy to infer that when you have the two hydrogens very close, the repulsion is high because you have the same charges closer. So you have this peak at the beginning. When you make the atoms far away from each other, you find an optimal distance. That's the distance of the chemical bond. And chemical bond is important to our life. We're just alive because we have chemical bond in this world. And if we make them even further away from each other, you lose this interaction because the two atoms will be isolated now. That's why you have the curve becoming flat. So this is the understanding of the Schrödinger equation for the hydrogen atom and how this affects the potential energy surface for a very simple problem. But life is not easy, and our problems mostly depends on multi-electronic systems, not only hydrogens binding each other. And what do we do then? Because we need to model the Hamiltonian and the wave function for these multi-electronic systems. That's a big problem. And all of those researchers were trying to find a solution for this, even in numerical methods, computational methods, and so forth. So we start by approximating the wave function by a product of the molecular orbitals we have in our molecular system. And we will call these molecular orbitals psi. And the molecular orbitals, as we already know, are linear combinations of atomic orbitals, which is great because we know how to deal with linear combinations. In these linear combinations, we decompose the molecular orbital into the contribution that each atomic orbital in the molecule has to the overall picture of our molecular system. That is great. So we have the contribution coefficient and the atomic orbital itself. And we approximate our atomic orbital into Gaussian functions. And we know how to deal with Gaussian functions because we know that if we multiply Gaussians, we have a Gaussian. And that helps us to compute the energy and the functions over these atomic orbitals. And we represent that as basis sets. So moving forward, now that we defined each element in our Schrödinger equation, it's time to say that this is a partial differential equation. And one of the methods we use to solve it is a variational method. And there is a very specific way of using this variational method, and I will explain better now. One of the approximations we have to solve the Schrödinger equation is the Hartree-Fock approximation. So now it's important to pay attention because we will change our notation. And our Hamiltonian now will be a Fock matrix, and this is represented by NF. And now our wave function is a pseudo wave function. It's called C. And we also compute the overlap between the orbitals in the molecule, and it's represented in pink. So now we will expand each of these terms again. The Fock matrix has a new element now. It has the kinetic, represented as T, the V, representing the potential energy, and a term called P. This term called P computes the repulsion between the electrons. And when you expand each of these elements and each of these integrals, you have in the Hartree-Fock equation our new Schrödinger equation to approximate for multi-electronic problems. You have the integral over the two orbitals, I and J. And then if you take the kinetic integral, you have the same kernel And this is important because we will use this to compute our integrals at the end. You have the same kernel as you have in the overlap integral, but you have a Laplacian operator in the middle to take out the kinetic energy. And after that, you have your potential energy, and you have quasi-Coulombic operator, and you depend on the charge of the system, and you depend of the distance between the electrons and the nuclei as well. And you now have the p element that computes inside of it the repulsion between two electrons of the same charge. We have now the big picture of how to approximate the Schrödinger equation, important for all physical properties we want to compute computationally. And now we need to understand, what do we do with that? How do we program and code these expressions? Over the years, many different ways of computing this were developed. And we go from very simple methods based on molecular mechanics to semi-empirical methods, to DFT methods, very famous nowadays. A lot of people using DFT. I showed the examples before of works using DFT for molecular and drug discovery. And we have the first principle methods. We have what we call the ab initio methods that solve all these integrals without parameterizing them. And those are very, very expensive. And as the previous talk mentioned, they scale exponentially. And if you were to take a large system, a polymer, for example, and you are to use a quantum mechanical method from first principles to calculate, you probably won't have enough time in the universe or space in computers to store all of this. So it becomes quite challenging to use ab initio methods for large-scale simulations. And that's why nowadays people develop machine learning, develop other types of potentials. They use molecular dynamics, other methods to overcome this intrinsic problem. And thinking about that, we know already that Julia is quite performant and Julia is quite efficient on computing numerics, on computing things that are costful in terms of computations. So what I did, I developed a package called Quantum Foca that calculates the integrals that build this Hamiltonian and allows us to calculate the Schrödinger equation. And this package is well documented. It has a very cute logo. Let me put the video here. So the cute logo. A fun fact. So in Portuguese, seal is called foca. That's why I call it Quantum Foca. So it's a joke to make it fun. And I hope next year at the JuliaCon, we will have stickers for Quantum Foca, hopefully, because they're cute. And using this package, I developed a graphical user interface to interact with my package, using it as a backend. So in this graphical user interface, you upload the coordinates of your molecule or your system of interest. As I'm doing here, I will show water because I think water is everybody's favorite molecule. And you upload the XYZ files you see in the text box, and you can select atoms, you can delete atoms, and you can play around with this representation. I know, you can ask me, where are the chemical bonds? this will be in the next release, I promise. And you calculate the molecular integrals and you calculate the energy of the molecular orbitals by clicking on Start. And it's quite fast. You calculate and you visualize this. The visualization is made with WebGL and JavaScript libraries for three-dimensional visualization. This shows the interoperability of Julia to work with other languages as well, using the Quantum Foca as a backend and to do the calculations. Oh, here, if you want to use only the backend, it's also possible, which is quite cool because you can open your repo and you can use the package, you import it, and let's say now you want to calculate the integrals for benzene. So you upload as a molecule and you upload the XYZ file. So this is me trying to find the file. Yes, I found it. Great. So you see the molecule. You have the atoms, the coordinates, and these are our structures in Quantum Foca. And you can interface with Atoms base. So it's great. Thanks, Professor Curtin, Michael. And you can see the atomic numbers. And if you want to calculate with STO3G, you can build the basis set for your molecule, in this case, benzene. And it will give you structures for the Gaussian basis set for each atom. And from here, you can calculate the integrals. So this is me typing, trying to do something. Let me figure out what it is. Okay. I think this video is clipped, but there is another part of the video, I think. Yes. So from here, now it's quite easy to use because you form the molecule. And after forming the molecule, you can just type overlap, kinetic, attraction, and repulsion. And you see it's quite fast. So it's quite easy to calculate the integrals. You see, it's very straightforward for the benzene. So it's very readable. It's very well documented. The documentation was written with Documenter.jl, everybody's favorite package. And I want to announce that the next release will be out in August 1st. And we will try automatic differentiation. And I want to call everybody to try the new release because I like feedback on the code to make it better. And I'm implementing automatic differentiation in the SCF part and GPU support for the integrals. And that's innovative because we usually have GPU support for some of the electronic structure methods like TFT, Hartree-Fock, but you don't have the GPU support itself for the molecular integrals because most of the packages they are parallelizable, but they don't have GPU support. So Quantum Foca will have GPU support in this next release. Before I do the acknowledgements, I think I still have some time left. I will show some fun facts. So as I explained, Foca in Portuguese is seal. And the joke behind it is also because we have a very famous package called Orca. And I was like, can my module written in Julia beat Orca, Orca's module to calculate the molecular integrals? In their version 5.0, they use a module called Shark. So will the Foca be faster than the Shark and the Orca? So that's an interesting question. So I've analyzed the scaling of these molecular integrals. When I calculated it in parallel for series of molecules like pentacene, tetracene, anthracene, naphthalene, and benzene. And I analyzed how this scales in one and more cores for these molecules. And you see that the behavior is quite close for 4 and 8 cores. But this is not the most interesting result. And I also analyzed for smaller molecules like ethanolamine, ammonia, ethane, methane, and water. But the interesting result is here. For the new release, I've tested the molecular integrals package against Fortran and C++ code with the same formalism that I used to implement on Quantum Foca. And for this, you can see that Julia beat both Fortran and C on this. And this is something I'm still figuring out, trying to understand the details why, but one of the facts is the architecture of Quantum Foca. And in this new release, this will be even more optimized. And I will explain the architecture in a second. Also, here I show the direct comparison for parallelization in Quantum Foca for 1, 4, and 8 cores. And the curious fact, going back to this plot, is that Orca is the C++ comparison that I'm doing. So Quantum Foca, so far, in the molecular integrals part, could beat Orca, which is quite cool, because the seal is that cute animal and is beating the Orca. And talking about the architecture itself, as I explained before, I took the overlap integral as a kernel to calculate the other integrals, the T, V, and G, the repulsion, attraction, and kinetic integrals, because all of them contain the overlap integral anyways. And this helped me avoid nesting for loops, and this reduced the cost of calculating. So you can use the multiple dispatch in Julia to overload the operators in the overlap integral and then getting the results. And after that, and this was for comparison, because the focus of the package is the molecular integrals implementation, but to get a property out of it. And I calculated the energy of the systems as well. And to calculate the energy of the systems, I built the Fock matrix that gives me the Hamiltonian and did a diagonalization. And then you calculate the energies, you analyze the convergence based on the threshold the user established. And then if this threshold is met, you reach the convergence. If not, you do the process over and over again, iteratively. So I would like to thank my advisor, Professor Tomasz Kowalewski, my committee members. Here's my GitHub queer code again. I would like to thank the Pittsburgh Supercomputing Center and the NSF for funding the project with computing hours. And yes, I leave you with the demonstration again. Thank you.
Okay, we have a few minutes for questions.
Thank you very much for the talk. How big are the molecules that you can compute right now?
Sorry?
How big are the molecules that you can compute? For example, can you compute some small polymers?
Yes, I've tested on small molecules first, but now the idea is to test on conjugated systems, larger, but I don't have these results yet, but it might work as well. But the molecules are 30 atoms large. Okay. Oh, I have a question there.
there's also a package called Fermi, and this Gaussian basis. Like, it seems that you are re-implementing, or these things are in competition with each other. Is there some planned collaboration, or is there a reason? Like, how does it differ, I guess?
Yes, okay, that's a good question. I was talking with Michael about that before the talk. So one of the differences is that I implemented the graphical user interface, and I used my biomolecular integrals package, and the idea is to expand that. But after talking with Michael, I also thought, how can I use Fermi's interface to calculate the self-consistent field procedure, for example, and optimize my whole environment using Fermi. So it's a very cool idea to join things and use the best we have to have good tools. Yeah. More questions? Oh, yes.
What's the algorithm you're implementing? Is it a McMurtry-Davidson?
Davidson, yes, exactly.
Are there plans to? Do you know if other algorithms are going to be significantly?
The OHATA, for example, yes. The OHATA will be implemented as well.
But are there? I know that there are newer algorithms. Do you know if there's going to be a significantly speed up if you implement them over? I think the ones in Orca are not the McMurtry-Davidson, right?
Yeah, I implemented the McMurtry-Davidson because it's the one implemented in Orca, and I wanted to do a direct comparison, so I would need to implement the same formalism. And I think it's pretty efficient based on the Hermite polynomials you have expanded there. So I don't know if other molecular integrals formalisms emerge, they will get that many adoption as McMurtry-Davidson have, OHATA. Yeah.
Thanks.
We have time for one more very quick question and quick answer. If not, let's thank the speaker again.
Okay, thank you so much.
And let's have our next speaker set up.
I would think he would like to wear a mic because he's going to be live coding.
I only have 2 mics. I can't do.
Can I hold this one and he wears that one?
No, because for the Q&A.
Oh, then we'll do the wearing one.
You can't pass the wearing.
Oh, you can't pass the wearing.
Yeah. So maybe this one's
Okay. Well, hello everyone. We're gonna rewind the slides back to the beginning. Beautiful. Okay, so I'm Aaron. This should pick up in a second. And this is Aditya. We're gonna be this is gonna be interesting because we were gonna try to do a live code demo during this with holding the mic. Should be fun. Cool. So I'll just close this out. Okay, so yeah, I'm Aaron, and this is Aditya. We're going to be presenting our package today, Piccolo.jl, which is an integrated quantum optimal control stack. So I'm at the Robotics Exploration Lab, also at Carnegie Mellon, and Aditya's in the Schuster Lab, which was at Chicago and is now at Stanford, where we've been testing some of this stuff on hardware. So like many of you guys, I'm sure recently, or some of you guys were recently in a movie theater asking some big questions about life. Like, where is our civilization headed? What does mortality mean? How can we be forces for good in the world? Of course, I'm referring to Barbie. But I'm not going to answer any of those questions today. I'm going to answer some questions about where is quantum control headed? What does direct optimization mean? And how can we go beyond models and actually run stuff on hardware? So first off, like, where is quantum control right now and where is it headed? So this is actually a device that we started testing on. This is what we'd call a quantum flute, or not really. It's a cavity QED device that was at University of Chicago, where basically the photons live inside of this this like physical device, which is pretty big, and like they basically resonate inside of this. And do you have a question? Oh, sorry. Yes. So this is a device that requires some novel control methods. So we tested on this, but we're not going to get into the results of that. If you want to see that, you can see the paper. So quantum optical control basically revolves around pulse optimization. So we have a model Hamiltonian, which is composed of a drift term, as well as drive terms and a drive pulse. And we're going to optimize over that pulse. So conventionally, what people do is optimize some objective that's just a function of the controls. And this is what is known as indirect optimization, because we're not optimizing over the states, which is what we really want to drive. We're optimizing over the controls. So what this looks like is usually this kind of nasty looking function intentionally, which is 1 minus the fidelity. So this is like the fidelity metric, fidelity objective. And then this nasty looking thing is the rollout from the initial state to like a final state. And we're calculating the fidelity with respect to some goal state, X goal. And I'm in a robotics group, so I use X to represent states and U to represent controls. So what is direct optimization? So we do something called direct collocation, which involves minimizing now an objective that's over the states. So it's over the controls and the states. It's a joint optimization problem over everything. And this allows us to easily write out a more simple objective. We're only concerned about the objective over the final states. But then how do we enforce the dynamics? So the dynamics come in via nonlinear constraints linking time steps, k plus 1 and xk, where like you basically propagate forward the xk with the controls to the next step. So these are applied constraint like time-wise on each step, which is a different formalism, and nonlinear solvers can take advantage of this, which I'll show kind of how that works. In this formalism, you can also apply constraints directly on the states, which is very handy for certain things, which we'll show later. So what this looks like inside of the optimizer is the optimizer is kind of figuring out, this is like a state trajectory. So at a certain like initial point, like you have an xk, and then you're going to propagate the xk forward to the orange point via the propagator. So that might not line up with like xk plus 1. So these brackets indicate like the dynamics violations of those constraints, which intermediately in the optimizer is not going to zero those out initially, but at convergence, these will all be zeroed out. So this is like the direct collocation optimization framework. So what is in direct methods versus indirect methods? So indirect methods, like you have to remain in reality. You have to stay feasible trajectories. You're rolling out. You're never leaving the dynamics manifold. And this isn't great. You might be a little sad about your existence. But like in a direct method, you can escape reality and travel between the infeasible world and the world of feasible solutions. So like I'm going to kind of demonstrate what this looks like with a little diagram where this green region is the space of feasible trajectories. So this is like the whole space of all possible trajectories. The green region is the one where the dynamics are satisfied. So the controls roll out to the states. So we're going to start in this purple smiley face, and we want to get here. And there's like some local minimum that we imagine in between. So like an indirect method is going to take steps, gradient descent steps, inside of the constraint, inside of the feasibility manifold. And it might get stuck in a local minimum and might not converge. A direct method, alternatively, can leave the feasible zone and land back leave the feasible zone and land back in the feasible zone at convergence, which is nice. It can jump around this, avoid local minimum. You can also just start totally outside. You can just initialize random trajectories, random controls, random states, and then end back in the feasible zone. So that's like direct collocation in a nutshell. It's not something I don't think anyone in quantum control does at the moment, pretty much just us. Okay, so then there's our kind of spin on this collocation framework, which is kind of acknowledgement of, since our dynamics are now implicit at each time step, like, and this dynamics for quantum people is an exponential propagator. So you can approximate, the way your computer actually calculates an exponential is, I don't know if anyone's read the paper, like 20 ways to calculate the matrix exponential. There's a lot of different ways. One of those is known as the Pade approximant for the matrix exponential, which kind of has a forward term and an inverse term. And these are like polynomials in the matrix polynomials. So in this way, like you can look at this, and this is a nice way to calculate the matrix exponential. In the implicit form, we can simply, instead of doing this costly inversion, we can simply move it over to the other side of the x clearly plus 1, which allows us to do our dynamics calculations like much more efficiently. And we pre-compute a ton of stuff inside the package, and this is where Julia really came in for handling these nasty Jacobians and Hessians, and everything's nicely handled in this formalism. Okay, so this is all detailed in our paper, Direct Collocation for Quantum Optimal Control, where we show like basically the theory behind this, and we test this on this circuit QED system with like state-of-the-art results. And this is kind of like what a trajectory looks like via a pulse from our solver. So that was pretty much a way to do quantum optimal control with a model Hamiltonian. So what if like we run the pulse on the hardware, and the hardware like gives a result that isn't optimal? Like there's some model mismatch error. So coming from robotics, there's a nice way to handle this, and this is something called iterative learning control. So what you're seeing here is you're looking up your lap numbers. So this drone is trying to track a figure-8 trajectory. And that you'll see, so lap 31, we're just gonna restart in a second. So lap 1, it's doing a pretty crappy job of tracking this trajectory. And it's like making measurements of its position, its velocity, and it's noticing that it's not doing a great job. And after each loop, it's like computing an update to its controls. So by lap 30, it's pretty much right on the figure-8. So this is an ideal called iterative learning control, which there's been like some limited like tests and simulation and stuff. Actually, Andy back there has written a paper on this for a certain case, but we're working more on this in this collocation format too. So in the quantum case, like there's some extra considerations. So we start with nominal controls. We get a nominal control pulse. We run it on an experiment. We measure it, and these measurements are noisy, projective, and very costly. And we don't want to measure the full stakes. That's super costly at every time. And anyway, we make our measurements. We compare them with like the nominal measurements coming out of the solver, and we get some measurement mismatch error. And we're going to use those updates, that error, to compute an update to the pulse using the hardware and our model, which is like kind of different than a reinforcement learning framework where you're not using a model at all. Here we are, and this leads to like sample efficiency improvements and just a better way to probably handle this problem. And so that's going to be demonstrated in code actually in a little bit. Okay, so before I hand it off to Aditya to do a code, I'm going to go over like the Piccolo.jl package, which is a meta package actually that has 3 packages underneath. So it has this package named trajectories, which was birthed out of a lot of pain handling indices for tons of different trajectory components. So this handles that very nicely and efficiently and gives a lot of neat functionality that keeps getting added to as we discover new needs. And then quantum collocation is really the workhorse of the collocation framework, which interfaces with IPOP.jl to do the nonlinear solver, the nonlinear solves underneath. And then also we have quantum iterative learning control.jl, which just got registered yesterday. We had another package that was registered, but this handles the ILC format, which I didn't get into the math, but we are going to demo it in code. So I'm going to hand it off to Aditya.
All right, yeah, so let's switch to the live code demo now. Yeah, I wasn't expecting to have to do this with one hand, but we'll see how it goes. Is that, oh, sorry? I think it's okay. Can everyone see that, or? Oh.
You want to do it?
Yeah, we can do it. Okay, yeah, we can. Can I just put this in my pocket, or? Okay. Is that good? All right, sounds good. Okay. Can everyone see this, or I probably should make it a bit bigger. Okay, yeah, so let's sort of look at sort of a very simple toy example just to demonstrate how like our whole Piccolo package works. So okay, let's just go ahead and like load everything in first. And so here we're just going to consider a very simple like 2-qubit Hamiltonian in like a rotating frame just to make things simple for us. And so here in the rotating frame, all that's going to be left is this coupling between our 2 qubits, and that's the first term. And then our controls are just going to be these direct drives on the qubit. And so here we've written things in terms of like creation and annihilation operators, but you could also equivalently write them in terms of Pauli operators. And you can think of that coupling as sort of just like a ZZ coupling. But okay, so let's go ahead and build this system. So we've gone ahead and defined our Hamiltonians as well as the different drive terms that we have access to control our system. And so once we've sort of defined the system, we can then pass it to this. We can set up this quantum system object that's just going to store our model of our system and go ahead and build this system. So the task that we would like to consider today is just a C0 gate on our 2-qubit system. So we should tell Julia what a C0 gate is. And so there we go. That's a C0 gate. And then okay, let's sort of define a sort of like initial guess for how long our pulse might be. So we're going to say it's 15 nanoseconds long, and we're going to use 100 different knot points in our trajectory, or like 100 different time steps in our trajectory. And so each delta t is around 0.1. And so this is also a bit important because we are going to use like a 4th order Pade approximant, and so you kind of want to. You also have to be a little bit careful about like how big you make your time steps relative to your controls in order for that to accurately match the actual exponential dynamics. Okay, and then now we're going to say that we have some bounds on our controls, so we can't drive it more than 17.5 megahertz, and then also we want our controls to be somewhat smooth. So we're also going to put a constraint on how big the second derivative of our controls can be. Okay, great. Now that we've sort of set up the problem, we should actually go ahead and like actually build the problem. And so to do that, we're going to use this unitary smooth pulse problem constructor. And so this is just like a handy like template that is able to build problems for us. But you actually have much more lower level control of the problems if you want. And that sort of functionality comes in through named trajectories as well as some other more detailed ways to construct these problems. But here we're just going to use this unitary smooth pulse problem to build our problem. And the one important thing to note here is that we've put constraints on delta t as well as this time step all equal constraints. So actually what the solver can do in this case is actually a free time problem, which is also especially hard with, it's harder with these indirect methods. But in our case, we're able to satisfy the dynamics, we're able to both adjust the controls, the states, and the time step. And in order to make sure the solver doesn't take advantage of any kind of discretization error, we need to make sure we put some bounds on delta t so that it can't make delta t either too big or too small. And then for convenience, we're going to say that all the time steps need to be equal, just so that we have like a nice sort of evenly spaced trajectory. So now that we've set up this problem, I kind of want to show off some of the features of named trajectories.jl, which came out of this problem of having to index into trajectories if you want to sort of get some component of them. So earlier, like trajectories would be stored as these like matrices or these vectors of vectors, and if you wanted to get the controls, for example, you would need to like make sure you are like being careful about how you're indexing into the trajectory. But now we just have these different names for each of the parts of our trajectory. So the first part is this unitary that's stored as like a real vector. So it's like an isomorphic real vectorized version of our unitary. And then we have these other 3 components, which are the controls, the derivative of the controls, and the second derivative of the controls, and then finally the time step. So now if you want to sort of access any of these components, it's just as simple as sort of calling like traj.a to get the controls. And then here we can now take a look at what the total size of this problem is. So we have 100 time steps, and then so the total problem dimension here is 4,500. And these are like all the different things that the optimizer has control over to solve the problem. Okay, the next nice part about named trajectories is that it makes plotting very easy. So we're going to go ahead and feed it the trajectory. We're going to plot our states, which is this isomorphic unitary, and we're going to plot our controls. And then we're also going to tell it to ignore labels on the states because this is plotting like 32 different elements because it's like a 2-qubit system, and then it's sort of this isomorphic vector, so there are 32 elements when you take the real and the imaginary part, so then that's another factor of 2, and so there are 32 elements in total, and we don't want to plot a 32-element legend. So this is kind of what the matrix elements of the unitary look like, and this is what the controls look like when we first set up the problem. So you can notice here that what we've done is we've chosen a random initial guess for our controls, and then for the unitary, we've set up, we've basically chosen this like geodesic from the identity to our C0 gate, and that is sort of the initial guess that we give it for the unitary. So in practice, you can give it whatever initial guess you want. We just find that this like geodesic initial guess for like unitaries in particular works pretty well. But now you might say, okay, this is kind of hard to see, so maybe I want to like look at some other nice part of this trajectory. So what I've done here is we can use this transformation feature in our plotting function. And so here what it's going to do is it's just going to convert our vectorized unitary to the actual unitary, take the third column, and then look at the populations there. And so now we can, for example, see what the evolution of the 1, 0 state looks like under our initial guess. And you can see it goes from 1, 0 to 1, 1 as it should under the C0 gate. Great, so now that we've set up the problem, we should go ahead and solve it. So this is going to solve the problem. It's going to call IPOpt. And you can see that as this sort of runs, the objective is decreasing. And in the second column is sort of the constraint violations. And you can see that that is also decreasing as this runs. So I let this run for like around 100 iterations. So this should like finish in a few more seconds. But yeah, essentially, this is sort of how you set up the problem and then let it run. Yeah, so this should so okay, it's terminated here. If we ran it for more iterations, it would reach convergence. But in the interest of time, I just sort of capped it at 100 iterations. Okay, so now if we look at the fidelity of our output, we see that we sort of have 5 nines of fidelity. And this fidelity function is actually taking the controls that are output by the solver, and it's then rolling out these controls and then taking the fidelity. So it's not just taking the final state from the trajectory and like looking at what that fidelity is, because that may in general be slightly different from the actual fidelity when you roll out under the matrix exponential. Great. Okay, so now that we have this, let's go ahead and look at what our solution looks like. So you can see it's different from the geodesic solution. And then here is our actual pulse for achieving the C0 gate. And then again, let's look at what the evolution of the 1, 0 state looks like. So under our pulse, we see that the 1, 0 state goes to the 1, 1 state. So that's all. That's good. Okay, so now we have this like nice nominal solution for our C0 gate. But then maybe you want to ask, like, okay, how fast can we actually do this C0 gate without sacrificing fidelity? And so this is another place where this whole like nonlinear program framework comes in useful, because we can then put a constraint that tells us that the fidelity of our final unitary cannot drop below some minimum fidelity. So let's say we want to sort of maintain 4 nines of fidelity. We can go ahead and build that enforce that constraint, and then use this unitary minimum time problem feature to sort of very easily build this minimum time problem. And so now, once we've built this minimum time problem, we can go ahead and solve it. And so what's happened here is that in this minimum time problem, we've added a term to our objective that basically looks like the sum of all our time steps. And so that's basically putting a penalty on the total length of the pulse. And so using this framework, we're able to both say, like, OK, we don't want to sacrifice fidelity, and we also want to go as fast as possible. And so once we run that, and then now look at the solution, we see, OK, we maintain 4 nines of fidelity. And let me go ahead and plot this really quickly. And so once we look at the solution, we can see that it's faster than before. And also, it's a lot more bang-bang than it used to be. So it's sort of maxing out the control bounds as much as it can over the course of the trajectory. Great. OK, and then finally, if we want to just check how much we improved, we see that from our nominal solution, we've sort of improved by 1.3 nanoseconds, or like around maybe like 10% improvement in our minimum time solution. Usually, this is more useful for like cavity QED systems. We're able to get like much bigger improvements using minimum time. But this is like a very simple toy problem with 2 qubits, so we don't see too much of a improvement necessarily. OK, now the next really exciting thing is that suppose that now we've gone and we've like gotten our minimum time pulse, then we go try it on the hardware, and it doesn't perform as well because there's some mismatch between our model and our actual system. So here we're just going to consider this toy example where there is mismatch of this form. So there are these Pauli operators in our Hamiltonian that we didn't know about, and so this is going to cause our pulse to not actually do the C0 gate as perfectly as it says it's going to do it in simulation. So let's go ahead and sort of just build this error Hamiltonian. And then let's go ahead and build these 4 states. So what we're going to do here is we're going to try our control pulse on this system with these error terms. And then we're going to make 4 different measurements. The 4 measurements are just going to be fidelity measurements on each of these 4 basis states. So on GG, GE, EG, and EE. And then using just these 4 numbers, we will be able to actually improve the pulse using iterative learning control. Great. So let's define the measurement. So this measurement is just the fidelity of the state at the end of the trajectory. And then we're going to go ahead and build this simulation experiment that uses this Hamiltonian that has some errors that were not in our original model. OK, so now that we've done that, let's tell it that we want to track this reference trajectory, which is our minimum time trajectory. So we're going to go ahead and do that. And you can see now that because of the errors that are in our new Hamiltonian, the fidelity has decreased to like 98.9% from like 99.99%. So that seems like a pretty significant hit to our fidelity. So we'd like to try to fix that. So we're going to go ahead and set up this ILC problem and then go ahead and solve it. And so this thing converges very, very quickly in like 5 iterations. And now if we go ahead and take a look at what happened, we can see that the fidelity of our pulse has improved from 98.9 to 99.5 using just fidelity measurements. So these are like very restrictive measurements that don't like have that much information about the state. In practice, you can also use like much more detailed measurements. Like you can do like full state tomography, and in that case, you can get much better improvements to your final fidelity. But those are of course very costly. So the fact that you can sort of get away with just making fidelity measurements is pretty cool. And so if we want to now see like what actually happened to the pulse when we ran ILC. It looks like this. So you can see it converges very, very quickly after just 3 or 4 iterations. And you can see it kind of like shrinks the pulse and like introduces these like small kinks in the pulse to make up for some of the modeling error that used to be there from these extra Pauli terms in our Hamiltonian. OK. And then we can just check again like what the infidelity is. We see it sort of goes down by a factor of 2. And then this one will just give us the percent change. And so we've improved by a factor of 2 here. OK, great. So that's sort of it for the live code demo. Before we end, I just want to talk about some future directions for Pico. So the first thing is that we can actually get some we can get some performance improvements from using a slightly more convenient way to represent this like isomorphic vectorization of the unitaries. So this like more convenient way means that the Jacobians and the Hessians have a slightly nicer structure. And we've sort of tested this, and it's sort of given us sort of 10% improvements in speed and memory when calculating the dynamics Jacobians and Hessians. And so actually this is not really future work because we already implemented it, but we haven't really pushed it into main yet. So but it'll be there soon. The next thing is this memorization of the dynamics Jacobians and Hessians. So there's actually a lot of repeated structure in our dynamics Jacobians and Hessians. And so if we can sort of memorize some of those computations, we should be able to get significant speed up, since like a lot of the bottleneck is in calculating these 3 things before we sort of feed this information to IPOpt. And then the next thing is that like higher order Padé integrators become kind of challenging to like analytically derive, but we spent some work sort of figuring out how to do this, like figuring out how to sort of hand code these derivatives. Currently, if you want to use higher order Padé integrators, it's going to just auto diff it, but we actually have a way to hard code them, so we're going to implement that soon as well. And that should also give us some speed ups for those harder problems. And then finally, or quantum collocation is going to have support for nonlinear controls. So what I mean by that is maybe in your Hamiltonian, you have a term that depends on a control alpha, but then you also have a term that depends on like alpha squared. And so it's going to soon have support for nonlinear controls as well. And yeah, that is sort of the end of the talk. Thank you. Yes. OK, that sounds good. Is it? Oh.
OK, let's open up to questions.
I might missed this in the notebook, but what's the qubit model you guys have? What's the qubit frequency, and are they anharmonic?
Yep. So yeah, it's just like this toy model. We're in the rotating frame, so the qubit frequency is like rotated out. So the only thing here that's sort of remaining is like this coupling, which is like 100 megahertz.
But are they anharmonic?
Oh yeah, so yeah, this is just like a 2-level model. So it's like super.
Okay.
It's like a toy example that we put in the notebook just to sort of demonstrate the different parts of the whole like Piccolo stack. But yeah, like in general, there are a lot more complicated problems that we solve with this whole this stuff. For example, like preparing like Fock states in a cavity, or other more complicated things like binomial codes and stuff like that, or even just like bigger systems. Yeah, and you can also we've also like tried stuff by modeling higher levels of a transmon or something, and that's all fine. This is just like a toy example.
Okay, but in general, it works for higher levels?
Yep. Yeah, the nice thing about Pico, quantum collocation.jl is that for the higher level stuff, there are like nice ways to like put like L1 costs on like populating higher levels, and then that turns out to be really nice if you want to sort of prevent leakage into higher subspaces. Yeah.
Other questions?
Yeah, just a quick one for me. So the method you're using for the time evolution looks like, to me, it sounds very familiar to the parallel algorithm to an extent. Have you heard about this one first of all? And then second of all, if you know about it, if like, could you maybe comment on if there's some differences and so on? If not,
what was it called again?
Parallel.
Parallel?
Essentially, you shoot multiple trajectories starting at different time points, and then you try to match them up.
So I have not looked at that. This is in particular not a shooting method. Is like the main point of this is like at any one time, like pretty much all these dynamic calls are actually called in parallel. Like they're all multi-threaded. So
Yes.
like you do not need to do anything shooting wise between it, which is one of the advantages.
In parallel, also each branch is evolved at the same time, and then you match up later.
Or like each branch, like I'm talking about between each time point, between each not point. So this is like the controls lingo. Between each not point, like that dynamics constraint is like each of these is given to the solver, and the solver evaluates them in parallel. Is that okay? I've not looked at this, so
Yeah, I would be interested to see if there's maybe some overlap.
Yeah.
But thanks for the comment.
No problem.
And we have a minute or two still left. If there are no other questions, let's please thank the speakers again.
Thank you, guys.
And with that, we adjourn the session. Thank you, everyone. And thank you for the AV staff for helping with everything.